Hello, is anybody there? A little bit early. We're going to start in about 6 minutes, so get a drink. Make sure you got the workbook printed, and then we've got a big session going on today. Hey, Tawonga, how's it going? How was paper 2? A lot of NMR. Okay, how do you think that went? Apart from that, how do you think it went? Okay, we're a little bit early still, got 3 minutes to go. Make sure you got a drink, it's a nice hot day, and we have too much NMR. Okay, I heard that Arrhenius equation didn't come up. Hamza, how do you think it went? Like, did you feel good about it, or was it like, nah, not for me? For low grade boundaries, fair. What was the NMR question? Was it some cyclic molecule, or have I made that up? First question was rates, but Arrhenius didn't come up, did it? Greetings, Robbo. I'm good. How are you? How did you find paper 2? Someone say it went all right, please. The maths was hard. Okay, cool. It was better for you than paper 1, do you mean? Greetings, FS. I would hazard a guess. Arrhenius, we have to see it, right? Paper 2 wasn't too good. You actually understood NMR for the first time in paper 2. Is that because of the cram? I'm not taking credit for it. I'm just curious. Yeah, no DNA stuff as well. But actually, I think we went through a lot of the stuff that did come up. We've got a hefty session. There are about 95 slides. And these are all paper 3 questions or variations of paper 3 questions. Shall we get going? Well, I've got a mixture of stuff that I've planned. I had a look at paper 2. I didn't have a look at paper 1. I didn't have a look at paper 1. I did have a look at paper 2. I had to go on student room. Wow. So yeah, that's why I know that Arrhenius didn't come up. So let's plan. If there's something I haven't gone through and you really want me to go through it, I will just take a detour and go through it, okay? So let's get cracking. I've done a lot of experiments in here. Obviously, it's paper 3, but just have a look at the breakdown of marks. 40 marks of questions on practical techniques in data analysis, 20 marks testing across the spec, can test you on anything, and 30 marks of multiple choice questions, okay? So let's get cracking. Let's get cracking. All right. So here we've got the formation of ethyl ethanoate from ethanoic acid using conch sulfuric acid. Nice, easy 1 mark to ease us in. What is the purpose? Can't remember now either, but yeah, I've got them from a variety of places. So what is the purpose of the conch sulfuric acid? Yes, it's an acid catalyst. That's it. Just catalyst will do. Done. Don't have to write anything else, okay? That's it. Any questions on that? If not, let's move on. Okay, due to the flammability of the reaction mixture, propose a safe heating method for step 1. All right, well, you got ethanol, and then you don't really want to be using an open flame, right, like a Bunsen burner, because of the flammability issues. So how could we heat this stuff up? Heating mantle, Alfie, correct? Done. Shall we move on? Yeah, you could use a water bath. I'd probably say heating mantle is the first thing that comes into my head. You could say water bath as well. You could say water bath as well. Yeah, water bath would probably work as well. So no issues there. No issues there. Okay. Any questions about that? All right, let's move on. We did this the other day. We've looked at this before. So when you see it, or if you see a question like this, you should be thinking happy days. Assume that the apparatus is properly clamped. Identify 2 errors in the student's apparatus setup and explain the issue caused by each mistake. Yeah, it could come up again. Could come up again, who knows? Oh, this drawing came up on paper 2, you're joking. Yeah, bung at the top is the first thing, okay? So that is 1 issue with it. So let's just draw that. We'll write that in. There's a bung on. What's the problem? So you get 1 mark for identifying the error for saying bung. And there's going to be pressure buildup as a result, right? So that's the issue. So that's an explanation of the issue caused by that mistake as well. It says, assume that the apparatus is properly clamped. So you can't make that assumption here, okay? Because it tells you. No, the condenser fully fits. Not a problem. Efes is right. The water is in, and Karis is right. The water is in the wrong way. So water needs to be going in this way. So water in at the bottom, you're going against gravity. It's called a countercurrent mechanism, and it is out at the top. Okay. That's identifying the problem. So that's 1 mark. What would happen if it was this way around? If water was coming out at the bottom, that would result in inefficient cooling. Inefficient cooling as the condenser. Would not be full of water. And if it's not full of water, it can't actually cool that down, okay? You're discussing paper 2, that's good. Right, that's it. That's where the 4 marks are coming from. So 1 for identifying the issues, then the explanation as to what would be the problem. Any questions about that? Let me know if there are. If not, we can move on. Shall we continue? Right, let's go. All right, question 1D. Explain the purpose of adding sodium carbonate to the distiller. Well, let's think about this. What type of substance can we classify sodium carbonate as? That's when I'm reading it, that's what I'm thinking. Sodium carbonate is a weak base. Absolutely. It's a base, it's a weak base. And the fact that it is a weak base, we can add it to remove or neutralize the acid. Absolutely, MK. And I bet. Yep, perfect. So it is there to remove or neutralize any excess H2SO4 acid. Electric heater, same sort of thing as heating mantle. Yep, get the mark for that for sure. Yeah, water bath would get you the mark as well. Excellent. And then that's the first reason, and it's a 2 marker. So it says, describe the reason for the pressure buildup in the separating funnel. Well, Aeromides got it. Absolutely, Hamza's got it as well. It's going to be pressurized due to CO2 being produced. Excellent. Okay. Pressure increase due to CO2 formation. Do you want me to go till 8 today? Is that okay? So technically we're meant to be going till 5:30. Happy to go to 8. If there is any takers for 8, let me know. If you want me to do that, happy to do that. Okay, cool. Lovely, let's do that. All right. I know people are going to put the England match on the side though, aren't they? Okay. All right. Question G. Okay, cool. The student adds 15 centimeters cubed of... Yeah, I'm happy. So I'm going to stop at 7:30. I'm technically should stop at 7:30, but I'm happy to go until 8 if you want it, okay? So I'm happy to just add another half hour. Or more if you want it, okay? If you think it's getting useful. If you think this is like too much, just duck out. Okay, so what is the first thing that we do? So we've got the volume of ethanol. Okay, and we've got the MR. We've got the mass of ethanoic acid. Cool, and we've got the mass of ethyl ethanoate made. Okay, because we got the volume of ethanol, we're also given the density. What quantity can we work out from the volume and the density? We did this on paper 2 as well. We can work out the moles. We can't do that straight away. What do we need to do first? Slant EP is, yes, find the mass, absolutely, because density is equal to the mass divided by the volume. So to work out the mass, that's going to be the density times the volume, which is equal to the mass. Is everybody happy with that? Yeah? All right, let's do that then. So the density is 0.790 times 15. So what do we get? 0.790 times 15. Is everyone happy with 11.85 for the first mark? Okay. Where do we go next? So we've got the mass of ethanol. I'm just going to label that as well. Once we've got the mass of ethanol, I've got the MR, so I could work out the moles of ethanol. Excellent. So that's going to be 11.85 over 46 to give me... I missed 2 questions. Where? I did miss 2 questions. I'll tell you what, I'll come back to those. I'll finish this one and then go back. Yeah, I did. I clearly just went too far. I'll get back to those. So that divided by 46, and that gives me, thank you for telling me, 0.2576 mole of ethanol. Okay, cool. Then where do we go next? I've got the moles of ethanol. Where do I go next? I've got to identify the limiting reactant, so I've got to use the mass of ethanoic acid as well to work out the number of moles of ethanoic acid. So the moles of ethanoic acid, that is going to be 7.50 over 60. So let's do that as well. 7.50 over 60. And I get 0.125 mole. Okay, so what's the limiting reactant then? What are we saying? I'm saying that this is the... Absolutely, this is the limiting reactant because it's a 1-to-1 ratio. There are fewer moles of the ethanoic acid compared to the ethanol. Is everyone with me so far? Just give me like a little nod or some sign on the chat that you're happy so far. Cool. Using the limiting reactant number of moles, where do we go? What can I work out? I could work out the theoretical moles of ethyl ethanoate. How do I work out the theoretical moles of ethyl ethanoate? I use the ratio, and because it's a 1-to-1 ratio, what are the theoretical moles of ethyl ethanoate going to be? Also going to be 0.125 mole. Absolutely good. Yeah, this is to work out the yield. We're getting there. There's just quite a few steps that you've got to take. Okay, cool. Once I've got the number of moles of ethyl ethanoate, how do I work out the theoretical mass? Absolutely nice. MK, lovely. So that's going to be 0.125 multiplied by the MR, which is 88. So should make 11 grams. I don't make 11 grams, but I know how much I did make. I made 8.21 grams, so my percentage yield is going to be 8.21 over 11 times 100. Is everyone happy with 74.6? Yeah? I get 74.6, 74.64. But lovely. Yeah, you can do the mole. You can do the mole version as well. I just thought I'd do it the proper way as opposed to taking any shortcuts. But if you're confident, you can do the mole version as well. As long as you're happy with how I've done that and your method and you get the same answer, all good. Any questions on that? That's a 5-6 marker, by the way. Okay, I'll go back to 1E and F. All right. Libel, was there no questions? Or you want me to explain something else? Okay. 1E, provide a reason for the formation of 2 layers in the separating funnel. Thank you. All right, why do we get 2 layers in the separating funnel? I mean, what are those 2 layers that we're getting? So we're getting an aqueous layer and the aqueous layer and true, but different. Yes. You get an aqueous layer and organic layer. So why is it that the organic layer sits on top? Well, the ethyl ethanoate is less dense than water. And because it's less dense than water, it will be at the top, and the water, because it's more dense, that's going to be at the bottom. It is insoluble in water, and because it's insoluble in water, you're going to get phase separation. So you're going to get an organic layer, a big line, and then you're going to get a water layer or an aqueous layer, okay? So you're going to see those 2 layers. You have to say that you get an aqueous and organic layer, and they do not mix or insoluble. They do not mix. And ethyl ethanoate. So ethyl ethanoate, less dense than water. So in your separating funnel, just as an aside, you're going to get something like this. You're going to have a tap there. So that's going to be your ethyl ethanoate. And that's going to be your aqueous phase, or water layer. Cool. And then what you can do is just open the tap. The water layer is going to fall out or drop out. and then you're going to be left with the isolated ethyl ethanoate. Okay, when you're doing this practical, where can you get some losses? What's going to happen? Are you going to really accurately close the tap exactly at the ethyl ethanoate layer? No, you could get some loss of the organic layer during the procedure as well, okay? So that could lead to percentage impurities, or percentage losses, I should say. Okay, finally, F. What is anhydrous CaCl2 used for? So now we've got our ethyl ethanoate. Yep, it's a drying agent, absolutely. So we've got our organic phase. There might be some water in there. So what we do is we chuck in CaCl2, and what that does is it absorbs the water. It's a drying agent. So it's used to remove water. It's a drying agent. Cool. That's one of its jobs. Why else CaCl2? What could another reason be for adding CaCl2? That it doesn't do what with your product? It's a relatively... Yeah, inert or unreactive. Absolutely. It'd be a crying shame if you added CaCl2 and it reacts with your product that you've spent so long to make and isolate, right? You'd be pretty miffed if that happened. Cool. How are we feeling about this first question so far? Let me know out of 10, like 10 being amazing. Yeah, it was a really, really solid start. Really, really solid start. Okay, cool. Right. A lovely little question for 6 marks. Right. Okay, cool. Just, we're going to practice that today. That's the whole point of today's session, okay? So these are all past questions from paper 3, varied obviously by me. Okay, question 2A. It's a 6 marker, okay? And what I'm going to do is quite a wordy question. I'm just going to draw out what happens, okay? So ethanoic acid looks like this. So there are 2 COOH groups on there, okay? So it's a diprotic acid, and 2 protons can dissociate, okay? And I'm just showing the first dissociation, okay? If you were asked, oh, in fact, I just said that. So why do we not get 100% yield? Transfer losses, incomplete reaction, and that reaction for ethyl ethanoate production is actually reversible, so you're unlikely to get 100%. Really, really good question, though. Okay, who would be like, yeah, 6 marks in the bag on this question? So use the concept of electronegativity to justify why the acid strengths of ethanoic acid and ethanoic acid are different. Okay. So I'll ask you straight away then. I'm just going to split my page up, okay, into ethanoic acid and ethanoic acid, and I'm going to draw them underneath. In the chat, can you tell me which acid you think is stronger? Okay, cool. I'm going to walk through it, but tell me which one you think is stronger, out of curiosity. So here's ethanoic acid, and here's dioic. Yeah, it is dioic. Good. That's a good start. So there is something inside telling you that ethanoic acid is stronger. And let's try and tease out why that is. Okay. Okay, yeah, but yeah, the fact that it's monoprotic, yeah, kind of. But let's actually look at the bonding, okay? Because the structure and bonding is going to give us an idea as to why that is. Okay. Now, oi, Romus, more H plus released. Okay, kind of along the right lines. All right. So we've got a delta minus and a delta H there. Does everybody agree with my partial charges on the OH of the carboxylic acid so far? Oh, Nathan. Okay, cool. Now, what is this CH3 group doing in terms of the inductive effect that we looked at the other day? Now, it's all to do with the inductive effect. It's positive, so it pushes electron density in, right? Okay, let's draw that in. Let's draw that in. If it's pushing electron density in this direction, what's going to happen to the magnitude of that plus charge on the OH bond? Is it going to be a bigger delta plus or a smaller delta plus? So it's pushing more electron density in this direction. Look at it. So what's going to happen to this delta minus? If this delta minus, we're pushing loads of electron density in this way, right? If that happens, this is effectively getting bigger, right? If that delta minus is getting bigger, what's that going to do? It's going to like stabilize that delta plus, right? Do you see where the logic's going with that? And let's try and put that into words. So I'm going to split my page up. So in CH3COOH, the OH proton is less delta positive. If it's less delta positive, is it going to be easier or harder to dissociate? I'm going to put two words there. Tell me which one is the correct word. Harder. Get in. Good. Yes, good. Does the logic make sense? Nice. Okay, and let's do the converse, okay? Let's do the converse. So let's have a look at here. What can we say about this COOH group? What's it doing in terms of electron density? You've got pretty much electronegative atoms here. So if you've got electronegative atoms there, they're not pushing electron density in, they're taking it away, right? They're electron withdrawing, exactly. So they're pushing electron density to themselves in this direction. Okay, well, if they're polarizing it, what does that mean for the magnitude of the delta plus on the OH proton? Is it going to be a bigger delta plus or a smaller delta plus? All of those electrons are going in this direction, look. Oh, that was meant to say delta minus. So that one's going to be... All right, cool. Hang on, I'm going to go back. Right. So it's all about the relative size of the delta minus and the delta plus. Okay, just so I'll go back through it, okay? So bear with me. So I'm just going to get a different color pen. Okay. Think of electrons moving. This isn't actually what happens, okay? But think about it like this. So there is electron density on the CH3 group. Do you agree for that bit? Yeah? And I'm just going to write down that the CH3 group has a positive inductive effect. And if it has a positive inductive effect, it releases electron density. Is everyone happy so far? Just let me know if you're happy with that so far. Okay, cool. Now, I'm going to get a highlighter. So with this yellow highlighter, if it's releasing electron density, do you agree that the electron density is going in this direction? Yeah? So the methyl group works via something called a positive inductive effect. It releases electron density, so it pushes electron density into that direction, okay? Okay, if it's pushing electron density in this direction, we're pushing negative charge in this direction, what's going to happen to that delta plus? Is it going to be a bigger delta plus or a smaller delta plus? if we're pushing negative electrons into that delta plus? Is it going to get bigger or smaller? And I think a lot of you got it. It's going to get smaller, right? It's going to get smaller. And the fact that it gets smaller, it's going to be harder to dissociate. What does the inductive effect mean? The inductive effect just means that certain groups can push electron density in a certain direction or take it away. So a positive inductive effect releases or pushes electron density in this direction, whereas a negative inductive effect, it does. And look, those electrons are going to be repelled, so they're all going to move in this direction, right? So the electron pair here, if that electron density is going to be moving in this direction. It's like a cascade effect. Does that make sense? So it's those repulsion of those CH3 electrons. Yeah? Okay. That's kind of a way to sort of see it. Exactly. Yeah, exactly. So positive inductive effect pushes electron density in. Now, consequently, let's just have a look at this molecule. And I'm going to tell you for nothing that this COOH group here has a negative inductive effect. Yeah, okay, yeah. Exactly. Well, actually, think about it this way. I'm going to draw some electrons in. Now, imagine you've got a big amount of electron density, and if it's moving in this direction, what's going to happen to this pair of electrons? They're going to be repelled, right? They're going to move in this direction, and what's going to happen to this pair of electrons? They're not going to be so much on the O. They're going to move closer to the hydrogen, okay? And that stabilizes that delta plus charge in a way and makes it smaller. And because of that, it's actually harder to remove that, okay? Because those electrons in the bond become actually less polar. Does that kind of make sense? It's hard to show it, but that's the logic. And let's try and use it for ethylene acid. So COOH has a negative inductive effect. Okay, well, what do we mean by that? Is it pushing electron density to the right or pushing it to the left to itself? First of all, let's get the language right. It's pushing electron density into itself, okay? It's withdrawing. Yeah, absolutely. Good. So the electrons are moving left. Does everyone agree so far? Good. So look what's happening to these electrons in the bond. If we're pushing that electron pair of OH more towards O, what's going to happen to that bond? Does it become more polar or less polar? That O is like taking those electrons because of that COH group. Bang. It's like a big tug of war. Have a look. So it was like this. If something is tugging on those electrons, do you agree that that pair is going to be over towards the oxygen like that? Because something is moving left. And if those electrons are moving left, in this sense, that delta plus is going to get bigger. Do you agree? So that's it for ethylene acid. Oppositely, for the it's okay. Positive inductive effect means pushes electron density in. Negative inductive effect withdraws electron density, okay? Right, do you want me to explain it one more time? I'm going to do it one more time. And I'll try and do like a little animation of it. Yes, no? One more time or allow? All right, cool. No, don't apologize. Don't apologize. It's a hard concept to try and get your head around, okay? And this actually helps for lots of other things, so don't worry too much about it. Okay. Try and copy exactly what I'm doing. Okay, there are electrons in these bonds. Put those electrons in like on a piece of paper if you've put it all in. So if your page is full of writing, just get a piece of scrap and let's try and do a drawing. circle that. Okay, this is a positive inductive effect group. And that releases electron density. Nathan, that is spot on. That is the same reason chloroethanoic acid is a stronger acid than ethanoic acid. Good. Now, that pushes electron density in this direction, okay? Now, remember, electrons are negative. So if it's pushing electron density in this direction, what's going to happen to this electron pair? Phoebe, you just have to know that some of these groups are positive inductive effect groups and negative inductive effect groups. And I'll show you why COOH is a negative one. Okay, but let's do ethanoic acid first. So if it's pushing electron density in this direction, what's going to happen to the negative charges in that bond? They're going to move right, aren't they? And what's going to happen to these electrons? They're also going to move right. So if they're moving right, it becomes less polar in a way. So it becomes a smaller delta plus. Does that logic make sense here? If you see it like that, that sort of cascading thing. Okay, here that's delta minus, that's very electronegative, and that's very electronegative. Okay, so let's circle our inductive effect group. So this is a negative inductive effect group, and that is electron withdrawing. So it wants to take that electron density because of those electronegative atoms like oxygen here. Now, tell me which way these electrons are going to move in this bond then. Because it wants the electron density in this direction. So that pair of electrons are going to go which way? Towards the carbon or the oxygen? Fariha, perfect. Sonma, absolutely. That moves left, right? Not left, right, but that moves left. This one also moves left. And if this OH group electron pair moves left, look, what's happened? That poor little hydrogen is feeling quite exposed. Its one electron is being pulled over by oxygen. That's being pulled over by oxygen. That becomes bigger. That becomes a bigger delta plus. Do we see the logic now? If that is a bigger delta plus, it's going to be easier to dissociate because it's more polar. Nice. Okay. Excellent. That's a tough question, not going to lie. That's a tough question, okay? So where am I getting any marks so far? I'm getting a mark here. CH3 is a positive inductive effect. COH has a negative inductive effect, getting a mark there. Okay, so in ethanoic acid, the OH proton is a less delta positive, so harder to dissociate. Yeah, that makes sense. Whereas in ethanedioic acid, so in ethanedioic acid, the OH bond is more polarized. And the fact that it's more polarized, i.e. bigger delta plus, so easier to dissociate. Okay, so I'm getting a mark there as well, and I'm also getting a mark for the correct drawings of both. I'm talking about those electrons are being pulled towards itself, those electrons are being pulled towards itself, those electrons are being pulled towards itself. All of those electrons are going to be pulled towards the electron withdrawing group, Fatima. Yeah? Even those OH ones, because this is acting at a distance. What's DW? Got no idea, Robbo. But Fatima, does that make sense? All of those electrons are moving. You get a mark for drawing the structures and having the correct groups on there, Simona. Okay. Cool. Right. Buffers. 5 marker. How are we doing for this? I'm gonna have a sip of water after that. I wouldn't suggest showing the movement of electrons like that. Maybe just get a bit of scrap paper just to rationalize how you're gonna structure your response. But what I would do is I would draw those out and annotate it like I have. That's what I would do. You don't get a mark for drawing the partial charges, but you need to talk about the partial charges for sure. So if you just draw the partial charges, you don't get a mark. You've got to effectively annotate it. All right. Okay, buffers question. How are you feeling about this? We should be thinking for a buffers question. Yeah, happy days, I think. So let's have a look. So you've got to calculate the pH of the buffer solution and give your answer to the appropriate number of sig figs. Okay, cool. I'm going to rewrite this, okay? I'm just going to shorten that as... Buffers are going to... No, you got to learn to love buffers, trust me. I'm just going to shorten ethylene acid as EDA. And I'm going to rewrite the equation. Okay. Right, HC2O4 minus plus H2O. Okay, I guess people in my class, what am I going to say, or people I've taught before, what am I going to say? What do we need to start doing now? No easy marks working out moles. Okay, cool. They haven't told you to work them out, but let's start populating this because what we're making is a table, right? So, how many moles of the oxalic acid do I have? Or the ethylene acid? I've got 1 times 10 to the minus 1. Does everyone agree? I just got that from the question. Put down the values given. Okay, how many moles of NaOH? 6 times 10 to the minus 2. Now, I don't have any of these at the beginning, okay? Don't have any of those at the beginning because they're the products. I'm just writing down my initial number of moles. Is everyone with me so far? Okay, so then I write down my final number of moles. But before I can do that, I have to work something out. What is my limiting reactant here? What's the limiting one? Fire away in chat, people. The limiting reactant is the ethylene acid or the sodium hydroxide. Is it? Is it EDA? Check those. No, don't say sorry, it's okay. It's the OH minus, right? So this is my limiting reactant. I've got 6 times 10 to the minus 2 moles. I've got fewer moles of this than the ethylene acid, okay? Why are you saying EDA? So that is, so 1 times 10 to the minus 1 is 0.1. 6 times 10 to the minus 2 is 0.06, okay? No worries. No, exactly. They are hoping that you're going to make these little mistakes, okay? So, you know when your teachers say that annoying thing, read the question, like really read the question. Okay, block me out sometimes. It's a bit irrelevant. Wouldn't the non-polar dissociate more readily since they have more van der Waals only and not dipole-dipole? No, the relative ease of dissociation is about the size of that partial charge on the OH proton. And the bigger that partial charge, think about it like an ionic compound, they're soluble because you've got actual formal plus and minus charges and they can easily rip apart to go into solution. If that bond is less polar, that's going to stay intact. It's harder to rip apart. It's going to need more energy to rip it apart because by polarizing it, you've almost done a bit of the ripping apart already. Okay, think about it that way. I don't know how to. So, yeah, I was going to try and rip that. That ain't going to happen. I haven't been to the gym enough. I'll try and get some paper and illustrate it in a sec. All right, so how much is that one going to go down by? Well, that's going to go down by the limiting reactant amount, right? And that one's also going to go down by the limiting reactant amount. So at the end, how many moles of the EDA are we going to have? Do you agree that you're going to have 0.04 moles of the ethylene acid and 0 moles of the OH minus? Good. Okay, excellent. Cool. What's going to go up as a result? Well, the salt is going to go up by 6 times 10 to the minus 2, i.e. 0.06 moles. We don't care about the water. Everyone happy so far? All right. Now, what do you notice here? Does it give you a volume? It doesn't give you a volume. So what are we going to do? So OH minus used is A minus form. Yeah, think about it like this. HA plus OH minus goes to A minus plus H2O. Yeah, same thing. Yep, absolutely. Yeah, the volumes are cancel out. The volumes are cancel out, okay? So let's have a look. Because I haven't given any volumes, yeah, that's all good. All right. So technically we should convert to concentration. So I'm just going to put this as over V and 0.06 over V to give me my concentration because I'm slow and I like putting it in. All right, now do you use Ka expression for this? Absolutely. So my expression for Ka is going to look like this. HC2O4 minus. By the way, can you hear that? Can you hear that train? Okay, so that's my expression for Ka. What do I need to work out? I need to rearrange that for what? For what variable? I need to rearrange that for H plus. Okay, so let's rearrange this for H plus. So H plus is going to be equal to Ka times the concentration of H2C2O4 all over the concentration of HC2O4 minus. All right, lovely. Everyone happy with this? And now what I'm going to do is substitute it in. We don't use the water because do you see an expression for water in the Ka expression? The water variable doesn't appear there. We don't have to use water. It's in such a large concentration, its concentration effectively remains constant. So I've explained what we don't use the H2O expression. Its concentration remains constant effectively. Okay, well, we've used the OH minus. We don't use OH minus here because the OH minus just got used up. Yeah, that is, I'm using an ice method effectively here. So all the OH minus got used up. However, if the OH minus was in excess, what would we have to do? Just as a little tangent, because people are asking. If the OH minus was in excess, we'd have to use KW. Good. Good. Because this will be a constant. You worked this out. And you'd rearrange it for H plus. Okay? And then you can work out the pH that way. It should be greater than 7. Cool. Right, so now let's sub in. Okay, I'll try and go up there. 1.05, you sure? KW at room temp is 1 times 10 to the minus 14. How do you know there is excess water? Will they mention it? It's all acid stuff is done in water. It's under aqueous conditions. So yeah, you don't need to take that into account. Sunma, I am going with you. So now I'm going to sub in. So H plus equals what? Ka is 5.89 times 10 to the minus 2 times my concentration of H2C2O4, which is my ethylene dioic acid, which is 0.04 over V, all over my salt concentration, which is 0.06 over V. The V's cancel out. Does everyone agree? Times 0.04 divided by 0.06. So my H plus concentration is 0.039, and then my H plus is just going to be the negative log of that. and I get a pH of 1.41. Well done if you got 1.41. Everyone happy with the buffers calc? It was only because somebody asked, Faz. Yeah, okay. Awesome, Ramos. Okay, so here, so just imagine it was slightly different, okay? I did work out the concentrations for the ethylene acid here, and I did work out the concentration for the HC2O4 here. So these are my concentrations. The number of moles divided by the volume. Priya, can you see how I did those? So I did over V, and I showed here in the working out that the V's cancel. So yeah, as Robo said, you don't have to show that, but I think it's good practice to put your volumes in. Okay, F, you good? Yeah? Okay. I'm just going to say, if this is in excess to work out the pH of a strong base, the pH of a strong base, you have to use the KW expression. Yeah, so Alfie, just to check, when acid is in excess, we use Ka, and when the base is in excess, we use Kw. Yes. The general equation for buffer calculations. Tell me more. This is how I would do a buffer calc, but you get so many different types of buffer calcs, it's hard to have like one general thing. I guess these are all the steps that I would take, given the information. Ah, gotcha. Okay, cool. So chemical equations, yeah? All right, I'll just do that here and I'll rub it out. So to make a buffer, we need a weak acid. So H plus and A minus, for example. All right, and because it's a weak acid, where does the position of this equilibrium lie? What are we saying? Yep, absolutely. It's a weak acid, so we've got a shed load of this. Of unionized HA, yeah? Okay. Now, we also need the salt of a weak acid. So the salt of this acid that we could use is sodium A. Abs, yeah, you got the right idea. So, if you take NaA, which is a salt of HA, what's going to happen if you take NaA and dunk it into water? Is it going to stay associated or is it going to dissociate? Well, it's going to dissociate, right? It's an ionic salt. Okay, so just imagine we've got a beaker. And in our beaker, when we're trying to make a buffer, we've got a shed load of HA. Phoebe, I would say the NaA fully dissociates. The weak acid partially dissociates, okay? So we've got a shed load of A minus. We've also got shed loads of sodium, but that doesn't factor into our buffers calculation, okay? So we've got a shed load of A minus. All right, so I'm just going to draw this out. We've got lots of HA, lots of HA. I've got lots of A minus from my salt. Okay, to make any buffer, I show you need a weak acid. So this is my weak acid. And you can pick any sort of the weak acid. So for example, a salt of hydrochloric acid could be NaCl. But if I use HA, a salt of HA could be NaA. That's just the counter ion, okay? And I get H2O in both cases. That's where that's coming from. So this is my salt of weak acid. Now you put that into solution, it's all going to dissociate. But I've got a small amount of H plus there because it's a weak acid, so it partially dissociates. Is everyone with me so far? So there are two scenarios now. So here is my buffer. So this is the weak acid, which I've got lots of. And this is my salt or my conjugate base, the A minus, which came from the salt of the weak acid, which fully dissociated, okay? All right, let's say I add some H plus to try and change the pH. So I'm adding H plus manually. If I add H plus manually, what is the H plus going to react with? It can only react with one of two things. It can only react with either the HA or the A minus. So what's it going to react with? It's a positive ion. Is it going to react with the HA or the A minus? It's going to react with the A minus. Good. Is there shed loads of A minus there to react with the H plus? Yes. So you add H plus. However, we've got shed loads of A minus there to counteract it. So the H plus that you're adding doesn't really contribute to the change in the pH because we've got a shed load of this and that just kills it, neutralizes it, bang. Do you see how that bit works? If you add OH minus to try and make it more basic, what is the OH minus going to react with? You guys are doing really, really well so far. Conceptually, we've done shed loads of stuff. All right, absolutely. You add OH minus, you've got lots of HA, and the OH minus can react with HA, like this. Alfie, correct. Oh, Alfie, you are right. It could react with H plus. You're not wrong. However, statistically, let's just look at this. Let's say you're adding OH minus. Yeah, there's a few bits. There's 2 protons there, but actually, what do we have more of that's more likely to run into? Wouldn't you say the OH minus is more likely to actually combine with HA as opposed to the few H plus ions we have? So you're not wrong. I think just doing it this way is a better way of doing it. So you'd make more A minus and H2O. So that's the general equations of a buffer. Can I rub that out? Are we happy with that? Let me know if you are. How was maths? Okay, HA will increase if you add H plus. A minus will increase if you add OH minus. Horrid. Okay. Why horrid? Can't have been that bad. All right. Need some feedback. Okay. Did somebody ask what happens, which way does the equilibrium move? Did somebody ask that, or have I made that up? Okay, cool. So I'm just going to make up a general equation now. So HA. Okay, so remember we've got lots of this and we've got lots of that. So if we add OH minus, what is the OH minus reacting with? Think about it reacting with H plus if you want. Alfie was not wrong. If we get rid of the H plus by adding OH minus, what's going to happen? The equilibrium is going to move right. So it moves right by adding OH minus. If you add more H plus, if you try and make it more acidic, the equilibrium is going to move left. So it moves left. Ah, what just happened? There we go. So there it moves. Yeah. Cool. If you look at it that way, I think just write all your equations out and you can work out which way it moves. You add H plus, it moves left. You add OH minus, it moves right. Cool. Right, can I rub this out? Oh no. Okay. Right. It's gone. Do you guys need a little break, or shall we continue with 2C, which is another calculation question and quite a hard one as well? What are you saying? Yeah, do this and break. Yeah, I'm happy. Yeah, cool. Guys, all right, wicked. Don't stress, don't stress. I'm happy to stay on after and just go through stuff with you, okay? I'm happy to just go through concepts with you as well if you don't want to do questions, whatever you want. So when you add an acid, yeah, when you add an acid, the HA increases. When you add a base, the A minus increases. MK, spot on. Perfect. Liber, you should know what the strong acids are. So your strong acids are stuff like hydrochloric, nitric, sulfuric. Your weak acids, they'll normally tell you. So weak acids with stuff going to be like ethanoic acid, chloroethanoic acid, ethanoic acid, but you're always going to get given Ka, okay? You're always going to get given Ka, and that's the indication that it's a weak acid. Aisha, thank you very much. Who else left the review? I know Aisha left one. Joking aside, yeah, carboxylic acids are mainly weak. But Nathan was right. You can make them stronger by putting on electronegative groups, okay? Please, if you could leave a review on Trustpilot, it'll be very helpful. It's really useful to the company as well if you think these sessions have been useful. So let me know if you're going to leave a review. Be much appreciated. Thanks, Aisha. Okay. Nathan, thank you. Say chemistry course was the best. Ovs. You're going to miss it. You're going to miss it. But it's a good feeling once they're all done. Okay. Let's grit our teeth for this question, okay? Let's grit our teeth for this question. So let's not get stressed. Let's not get stressed. Let's go through the motions. We know how to do this. No, you're not, Fariha. Stop it. You're going to miss it. All of you are going to miss it. Chatting. Right. During a titration, the end point was reached when, all right, blah, blah, blah. Determine the equation for the reaction that occurs and use it to calculate the original concentration of the ethanoic acid solution, okay? So when we're reading that, oxalic acid is ethanoic acid. It's a really, really good question, okay? Come on, it's not that bad. Do people think, I will do this question, but chemistry, people normally hate chemistry. They normally think it's the worst one. Is that true? And if so, can you just let me know why? I'm just curious. All right, so we've got to make some equations here, okay? Physics by far. Wow, chem is better than bio. You're a first. Inorganic. You hate inorganic. Wow. My world just came crashing down. It's right, not like I did extra studies in organic chemistry or anything. Right, equation. So, people obviously love biology more. Like, every school I've taught at, biology is the preferable subject. Robbo, there is. Inorganic's beautiful. Okay, right. Shall we have a break and come back to this? Sunma, take that back. Nothing wrong with liking chemistry. Don't worry, you'll smile in August. August is when you will smile, okay? Right, we'll take 5. Take 5. Okay, I'm just going to grab a drink. No, you're not. Come on, we need confidence. Guys, actually take like 5 minutes away from the screen, okay? I'm coming straight back. Just going to grab a drink. Hi everyone. What time are England kicking off today? Five, okay. Nathan, I've got pH curves on here as well. With half neutralization point. Liber, this is yeah, we got some back titration questions as well. We've got so many questions today. I just went through, just did a whole bunch of stuff, like lots of required practical stuff, obviously. EDTA. Here you go, half neutralization point. Just loads of different things. I think that will be useful and may come up. Because they can ask anything. By the way, I've done the worked answers to these. Who knows, Fatima? I mean, I've done the worked answers. If we don't get through these, they're already done. I'll just put them, I'll send them to the team and they can hopefully get those to you. So they're like more in depth than a mark scheme. These questions are quite long though, aren't they? I think we're spending longer on these than on the paper 2 questions. Did anyone actually like paper 2? It was not a bad paper. Good. Paper 2 was better than 1. Okay, cool. Good. Can we go over more practicals too? We're going to go over the practicals. There's 2 ways of doing it, and I need you just to think about what the best way is. I've done questions from the required practicals. I did get bored midway though. We can do the questions from the practicals like I'm doing now, or we can go through the practical sort of from scratch. I'm not sure what you think would be better. Come on then, let's go. 335, question 2C. Okay, so the first thing, scratch, yeah? Over questions, sure. We'll do a mix, but just honestly, like, tell me if we're like, the questions are too much, and then I'll try and do the practicals from scratch, okay? All right, let's have a look at this. So the MnO4 minus, that is going to be converted to what? What's that being converted to? In a redox reaction, in acidic conditions. We're going to be generating Mn2+. Good. Okay, so the oxidation state is +7 of the manganese here, and it is +2 of the manganese here. Transition metals and EMF I got planned. I've got some hard questions as well. Okay, so we need 5 electrons, because this becomes negative by 5. So it's a 5 electron reduction, okay? To balance up the oxygens in the MnO4, we need 4 water molecules. And we also need 8 H+. Is everybody happy with that half equation? There is another half equation for the oxalic acid that you need to know as well. So, oxalic acid or ethanoic acid is that. It's a diprotic acid, and during the dissociation, you get these 2 ions, okay? This is the ethanoate ion, and it can undergo redox reactions. So when you have the C2O42 minus ion, what can that be oxidized to? What can that be oxidized to? This isn't necessarily a practical question, but this is, you could say, redox titrations. So this is definitely from a redox. It's a paper 3 question, redox titrations for sure. So what are we going to make? CO2, absolutely. And we're going to make 2 molecules of CO2 because there is a 2 in the C2O42 minus. How many electrons are given out? Look at the charges. So 2 electrons are given out. Yeah, it's 2 CO2, good. And 2 electron oxidation, okay? Now, this equation number 1 needs 5 electrons, but equation number 2 is only giving out 2. So we need to scale up reaction 1 and 2. So we're going to multiply reaction 2 by 5, and we're going to multiply reaction 1 by 2. If we do that, have a look at what we get. Is everyone with me so far? So we need equal quantities of electrons, okay? So that's going to be 16H plus, and that's going to be 2Mn2 plus 8H2O. And equation number 4 is going to be 5C2O42 minus goes to 10 CO2 plus 10 electrons. Okay, what do we do to equations 3 and 4 now? Lovely. So with equations 3 and 4, now we've scaled them up to the right factor, we just add them up, okay? So if we're adding up equations 3 and 4, yeah, we combine them, good. So we cancel the electrons out. Are there any other species that cancel out? No. So that's going to be 2MnO4 minus plus 5C2O4 2 minus plus 16H plus goes to 2Mn2 plus 10 CO2 plus 8H2O. Why are we doing this? We're doing this to get the molar ratio of the redox reaction, okay? So it's a really important thing to do. Put a box around that. The rest is trivial. The rest is trivial, okay? That's the hard bit. So, step number 1, what can we do? We can work out the moles of MnO4. Hang on. So the gradient is minus EA over R. So whatever you get as your value of the gradient, yeah, gradient times 8.31, correct. So gradient times R, correct. Okay, back on track. So let's work out the number of moles of potassium manganate because I know the concentration and the volume. So the number of moles is going to be, and I'm going to label it, moles of MnO4. And that's going to be 20.2 over 1,000 times 2 times 10 to the minus 2. So that's the first thing that I would do. Right, so what does that give you? 20.2 over 1,000 times 2 times 10 to the minus 2. Do we get 4.04? Times 10 to the minus 4 mole. Yay? Okay, so I've got the number of moles of this. I need to work out the original concentration of the ethanoic acid. To work that out, I need to use the molar ratio. So the moles of C2O42 minus is going to be equal to that value, 4.04 times 10 to the minus 4, multiplied by what? So divide it by 2 and times it by 5. So I'm going to times it by 5 over 2. And that gives me 1.01 times 10 to the minus 3 mole. Agreed? Where do we go next? So I've got the moles. Yeah, times by 2.5. Absolutely. So I've got the moles of the oxalic acid. And I don't have the concentration. However, I do have the volume. So the concentration of H2C2O4 is going to be the moles of it, 1.01 times 10 to the minus 3 divided by the volume, which was 25. Hi, Nancy, how was maths? So I get a concentration of, excellent, Khadija, 0.0404 moles per decimeter cube. Excellent, good to hear. There you go. Sorted. Done. Any questions on that? Can I move on? Solid. Okay, lovely. Right, this is a required practical, so can't remember the number, but it's enthalpy type question, okay? So where you could get a polystyrene cup calorimetry or you could get a combustion calorimetry. So here we are doing a neutralization reaction. So let's just go through it. So a student did an experiment to see the temperature rise in a reaction between HCl and sodium hydroxide. So what they're doing is polystyrene cup. And do you want me to go through how you do this from scratch or not? MK it does, and it goes to 2 lots of Cr3+, okay? All right, so we take a polystyrene cup. Why polystyrene? Yep. And good insulator. Yeah, reduces heat loss to the surroundings. I'll be really quick for you. Now, what we can do is we can put that into a beaker and make it even better by insulating, by putting cotton wool or something around the outside. Good insulator. Everyone with me so far? And then, let's say I take a certain amount of NaOH. So I take a certain amount of NaOH, and then, just like when you're getting your coffee, or whatever it is you guys drink, and you go into Starbucks or Costa, your coffee normally comes with a what? To reduce heat loss to the surroundings. A 3-letter word, beginning with L. A lid. So we're going to put a lid on this thing to reduce heat loss to the surroundings. Exactly. Now, this is a special lid because there is a hole in there, and that hole is to make sure that we can get a thermometer in our sodium hydroxide. So there is our thermometer as well. That is our device to measure the temperature. Okay, so our DT is going to be measured by that thermometer. Okay, we all good? Then, what do you think we're going to do? Should we just take the other reactant and bung it in? I'd actually argue we shouldn't do that. What we need to do is make sure the temperature actually equilibrates, okay? So what we're going to do is measure the temperature of this for about 3 to 4 minutes, okay? And as we're doing this, we're going to plot a graph. So here is time in minutes. So at 0 minutes, 1, 2, 3. So let's say this is like 19 degrees C, okay? So we're measuring that, so making sure that the temperature equilibrates. So we just got NaOH in there to start. Now, what we're going to do at minute 4, we're going to take the lid off, and what do you think we're going to add into there? We're going to take the lid off and we're going to add HCl. So when they react, it's an exothermic reaction. So what's going to happen? We're going to stir it, and what's going to happen to the temperature on the thermometer? Yeah, it's going to increase, right? It's an exothermic reaction. We're going to get something like this. So we add it at minute 4, and at minute 5, minute 6, we see something like this, okay? Now, we may not exactly have a data point for the time of adding, so that's the time of mixing. Now, let's say we don't have a data point for the time of mixing. What mathematical tools could we use to get a data point for where we don't have a data point? Extrapolate the lines. 1 line or 2 lines? Because I need a straight line here through these points to minute 4, and I need a straight line going back to minute 4, right? Okay, good. So then for my time of mixing, even though I don't have a data point there, minute 4 was my time of mixing, and that distance there, or that difference, is going to be equal to dt. And you can see that's going to be the true delta t. Yeah? I wouldn't join lines there. I'd just do lines of best fit. One here and one there. Okay, at the moment in my graph, I wouldn't ignore any of them. They fit the trend. There are no obvious anomalous points. Not ignoring any of them. But the question that we're doing next might be different. Who knows? Okay, so I've got delta T. I've got the mass or the volume of this solution, because that's just going to be the mass of water. And I also know the specific heat capacity of water, which is 4.18 joules per grams per Kelvin. So I know everything to work out Q, because Q equals MC delta T. Yay? Is that kind of helpful? So this is called a calibration curve or a cooling curve. Cool. Let's have a look at the... I'm going to rub this out. You can go for it again if you want to. Let's go through the question now. So that was just a bit of background on this. You can use polystyrene cup calorimetry for endothermic reactions, for dissolving, for neutralization, displacement, stuff like that. Combustion calorimetry, obviously we use a calorimeter made out of glass or metal. For mass, you always use the mass of water, apart from in combustion calorimetry, when you're working out the delta H, you use the mass of fuel burnt, okay? Cool. Let's have a look at this. This was 5 marks. 5 marks for plotting a graph. I kid you not. What's it going to look like then? Okay, make sure you're actually doing this one then. So what's going to go on my horizontal? I've got time in mins. What goes on my vertical? I've got temp in degrees C. Okay, cool. So let's call that one 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Because there are 12, well 13 actually, time increments. Yeah. And then temp, let's start at 19.7. Let's start at 19.7. Okay, and then that's going to be 0.8, 0.9, 0.8, 0.9, and let's call that 20. Okay, then 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, let's do that again. 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 0.10. And that's going to be 21. Everyone with me so far? And then 1, 2, 3, 4, 5. I need a bit more graph paper. I need a bit more graph paper. Okay, but you'll get the gist. 1. Can we start straight from 90.7? Yeah, you can, for sure. 1, 2, 3, 4, 5. I'm just going to go 21.5. Okay, so if we plot this, so here's 19.8 at 0. 1, 2, 3. We don't have a data point. Can't remember what the mark scheme said. I actually can't remember what it said for would you get your graph? you might lose marks, not for starting at 0 necessarily, but your graph is going to be huge, okay? And I think you probably will lose a mark for starting at 0. You don't need to start at 0, okay? I would say, yes, you probably would lose a mark. The y-axis is the temperature. Yeah, you probably would, because your graph will be massive. And all your data points are just going to be like up there, right? So yeah, it would look bizarre. I guess the rule of thumb is you want to use more than half of the graph paper they've given you. So that's why start at 90.7 should be okay. Everyone happy so far? Okay, then keep on plotting the points and tell me what you're getting. So at minute 5, that's 21.2.3.4. Okay. All right. At minute 6, it's 21.7. So that's somewhere like here. At minute 7, somewhere like there. Minute 8, 21.5. Minute 9, 21.4. Then 21.3. Whoa. 21.5. And that's at minute 8. 21.5 at minute 8. Okay, cool. Then 21.4. Okay, so that one's wrong. So minute 5 is wrong. Okay. Cool. It's 21.4, then 21.3, and then 21.2. 11's 21.2, and that's 21.2. Okay. Sorted. Yeah, I know. On mine it doesn't work, but it should be fine on yours. Should be fine on yours. And actually, that one should say 21.1. It just doesn't work on my graph paper because I chose the wrong graph paper. But you get the gist, okay? So just try and go a little bit above. Now, I think Hamza asked a question. Well, let's have a look. If we're drawing this, I'm plotting one line of best fit there to minute 4. Okay? And I'm also plotting another line of best fit. But what am I not doing? Am I going to take into account this point? What do you think? Am I going to take that into account? No. Ignore it. It is anomalous, okay? So I am going to draw a line of best fit going up here. And I think when I did it at minute 4, I think that gets you to, I mean, let's just guesstimate, right? But 6, 7, 8, 21.9. And I think when I was doing it, I did get 21.9. So even with these little squares, you get a good estimation of what it is, okay? So you get 1 mark for line of best fit and plotting your points as well, okay? So what's delta T? So what's delta T going to be? So minute 4, my delta T is going to be what? What? Tell me how to work out delta T. It's going to be 21.9 take away 19.8. So delta T equals 2.1. Yeah, like 2.1? Absolutely. Good stuff. Lovely. So where are you getting the marks for? True lines of best fit. Plot all your points correctly. Okay? Make sure your axes are the correct way around and sensible scales have been used. Okay, extrapolation and final answer. 21.9. Take away 19.8. Perfect. The 21.9 came from here. I ran out of graph paper. But if that's 21.5, I'm guessing here, So that's 20.6, 0.7, 0.8, 0.9 from my extrapolation, Swanga. I ran out of graph paper, but that won't happen in the real exam. But do you see how that is a rough 21.9? And I think it is actually close to what I got when I was doing the questions. So that's where that came from. Yeah? Okay, cool. So we've worked out delta T. All right, that's it. But for 5 marks, when you see this, you need to be thinking what? Happy days. Okay, if you get a question like this, you should be thinking sorted. Okay? Any questions on that one? Speak now, or hold your peace and let's move on. But just going to say, before we go, scale, axes, plot points. This is where the marks are coming from. Extrapolate. And then the final mark for delta T. Okay, so that's where your 5 marks are coming from. Cool. Okay. Don't get any marks for adding a title on the graph. They've told you what they want you to plot. You've just got to work out the rest. All right, everyone's favorite. Hands up if you like a bit of uncertainty. I mean, no one likes uncertainty. No one likes change, right? But let's go through this. So, fire away in the chat. What would you say? And I'll tell you what the answer is. So here's delta T. Delta T was recorded as 2.1. Okay, so it's asking you to determine the percentage uncertainty for the temperature increase. And the temperature increase was 2.1, right? So that was delta T. That's how much it went up by. Okay, how are we measuring delta T? So here is a thermometer. Nathan, good. Okay, so the first reading was 19.8, I said. But 19.8 has an uncertainty of plus or minus 0.1. Do we agree? So there's an error of that much, of the 19.8. Let me know if you're with me so far. And then we're going up to, whatever it was, 21.9. But every time we take that reading, that's also got an error of plus or minus 0.1. So we're to get delta T, look at what we're doing. We're doing 21.9. Take away 19.8. Plus or minus 0.1. So what do we have to do? How many times does this uncertainty appear, this error appear? It's appearing twice. S Ninja, greetings. I'm guessing maths was good. It's appearing twice. So to work out the percentage uncertainty, it's going to be the absolute error multiplied by how many times it occurs in the reading or the measurement. So twice here because we're working it out by difference, divided by the value of dt, which is 2.1, times by 100. So what do we get? It's going to be pretty big, isn't it? It's going to be, yeah, 0.2 over 2. It's like 10%, isn't it? Yeah, 9.5. That's big. Okay, that's a huge percentage error. What do you think the next question is going to be, even without looking at the question? What do you think a follow-up question is going to be? How could you decrease the percentage uncertainty? Okay, well, let's have a look. Exactly. All right. So before we get onto that one, propose a modification to the experiment to reduce heat loss. Okay, I mean, we spoke about that. So one of those is use a polystyrene cup. They didn't use a polystyrene cup, so they should use a polystyrene cup. Uncertainty over value measured times 100. Absolutely. Yep, use a lid. Those are the two that come straight away. You only get 1 mark, but those are 2 options. Okay, propose and justify an additional modification to the experiment that would reduce the percentage uncertainty when using the same thermometer. Okay, What are we thinking? I'm just going to do this from like basic maths, okay? Uncertainty. And your maths is better than mine. Simona, it says with I think that would be too much. Okay, I think we're not getting to the right conclusion here. So let's think about the formula, okay? So we know it's 0.1 times 2 divided by, nice Fatima. Okay, so divided by delta T. And in the first scenario, delta T was 2.1, right? So what do we need delta T to be for the percentage uncertainty to go down? We need delta B to be what? Do we need it to be bigger than 2.1 or smaller? Simona, would you get bomb calorimeter? Nah, no bomb calorimeter allowed. Just a simple modification. Romus, if it was, yeah, it has to be larger, okay? So just do it on your calculator. Do 0.2 over 2.1 versus, I don't know, 0.2 over 20, right? You're going from 10% to 0.1%. Sorry, to 1%. So you're reducing it by a factor of 10. Yeah, so you want to be dividing it by a bigger number. Well, how do you get a bigger delta T? That's the question. That's really what we're answering. How do we get a bigger delta T? What could we do? So we want a bigger temperature change. We're getting a mark for that. We need a bigger temp rise. How do we get a bigger temp rise? What could we do? We're not heating it because it's polystyrene cup calorimetry. We're just mixing an acid and alkali. If you leave it for longer, it's actually going to cool down, right? The peak rise has already happened. Oh, what do you mean more volume of HCl? Because I wouldn't argue that would agree. Not the volume, but related to volume, where there's more stuff in a given volume. What do we... Higher conc. Yes. Higher concentration of acid and alkali, right? Good. Increase the concentration of acid and alkali. Okay, so that's how we do that. Why not by volume? Why not by volume? If the concentration remains the same, in fact, if you use larger volumes, are you not diluting it? Are you not making it smaller, the concentration? Yeah, there's going to be more collisions. There's literally more stuff. You got more moles of stuff, right? So the DT is going to be bigger because there's more stuff there, causing that temperature to go up. So that's why not volumes. I don't even think they'd give you any credit for saying volume. Yeah, absolutely. Increasing rate of reaction, and you're just going to have more stuff there. And every successful collision is going to result in that temperature rise. Okay, just by definition of having more stuff there. Okay, does that make sense? So what they're really saying is it has to be a reference to the moles. Let's say you increased the volume, but you kept the concentration the same, MK. Would that change it? Just by virtue of having more of it, but the concentration was the same? I'd still argue you wouldn't get an increase in the temperature rise. You need more of those particles there. So you need to have a reference to the concentration or the moles. No. Greeting. So just by increasing the volume doesn't necessarily increase the concentration. Have to be specific about the amount. Amount is referring to the number of particles there. Yeah, if you diluted it, you'd actually get a smaller DT because you haven't got much stuff there. Okay. Right. Question 3E. Whoa. Question 3E. So this is a... Oh, okay, decreasing the volume. So you're saying, but if you decrease the volume, you're going to have a higher concentration. Yeah, but so why not just say higher concentration is my point. If you're going with volumes, you're setting yourself up not to get the marks. I agree with you, Simona. But by decreasing the volume, you're actually increasing the concentration, I would say. Does that make sense? Hey, didn't you just get here? Right. Let's have a look at this question. Do you have maths? If you had maths, I'll let you off. Okay. We'll do this because it was late, and then the person who was going to do the booklet didn't do the booklet, so I did the booklet, and that's why. But anyway, right. It's our 5 marker. Let's go. Cramming. We'll do this question, then we can eat. Have a little break. Yeah, because I know it's rough if you just had maths. Yeah. Is everyone happy with that? Thank you, S Ninja. All right, cool. Don't know why they're calling me Unc. I know they call Neil that as well. Right. Someone used to call me Baji in the Easter revision courses. I don't know why, but they did. Anyway, so no, I like Uncle now. I don't get it, but I'll go with it. I'll go with it. Don't call me bro. Okay. Right. First, we got to do a balanced symbol equation. Yeah, but Baji, why were they calling me Baji in the chat? I have no idea. Right. Ethanoic acid. Yeah, they were. Right. So ethanoic acid is this. So H2C2O4. So that's what it is. Thanks, Aisha. That's very kind. And sodium hydroxide solution is that. Okay, cool. Make sure you guys are leaving some reviews. I'd really appreciate that. So, it sounds stupid, but what is the equation for this going to be like? Because they're expecting you to know this. So, what's the chemical equation going to look like? What are we saying? Remember, this is a diprotic acid, okay? For each molecule, there are 2 protons being released, and I'm adding a base to it. So how many molecules, or not molecules, because sodium hydroxide isn't a molecule. Yeah, it'll be 2 equivalents of base, right? So I need a big 2 there. Good. Those are going to be knocked off. So this is going to be Na2C2O4. And what is my other product going to be? My other product is going to be H2O. 2 H2O. Super. That's it, okay? That's our first step. Remember, read the question carefully. So that's the hard bit. The rest is trivial. Once you've got the chemical equation, it just is trivial. I want you to go in there with bags of confidence tomorrow, okay? Read the question, take your time, go slow. All right, where do we go next? We've got to calculate the moles of ethanoic acid, and we've got to calculate the moles of sodium hydroxide. So, step 1. Moles of, can I just call this EDA? So the moles of EDA, I've got the concentration and I've got the volume. So I've got 30 over 1,000 times 1. And does that give me 0.3? 0.03 even. 0.03 moles? Okay, cool. And then I need to work out the number of moles of sodium hydroxide. So then I'm going to put... Greetings, everyone. Hey, Anthony, how was maths? We're going to have a break after this question so the maths people can get some time. I'll run over today as well, so don't worry. So then I've got 50 centimeters cubed of 0.8 mole per decimeter cubed of sodium hydroxide. So 50 over 1,000 times 0.8, and that's 0.04. Okay. All right then. What am I thinking next? That should say NaOH. What's the next step? Step 3. What's limiting and what's excess? So I've got 0.04 moles of this, and I got 0.03 moles of the ethylene acid. Well, EDA is limiting, you sure? Oh, S Ninja's throwing a spanner in the works. Jazz, NaOH. I don't know, we got a mixture. What are we going with? Someone's got to be right. Okay, let's think about it this way. So we've got 0.03 moles of this. Look at the molar ratio. I'm going to times it by 2. So for every 0.03 moles of ethylene acid, I need 0.06 moles of sodium hydroxide reacting. However, do I have 0.06? I don't have 0.06. What do I have? 0.04. So NaOH is a limiting, yeah? Do we see why that is? NaOH is a limiting reactant. Yeah? Okay, cool. Yeah, exactly. So it's just these little things to be looking out for when you're doing the exam. Yeah, let's go. Come on. All right, where do we go next? Where do we go next? Well, think about it this way, Nathan. So you've got a 1:2 ratio. I've got 0.03 moles of this. So for every 0.03 moles of that, I need 0.06 moles of NaOH, but I don't have 0.06 moles. I've got less than what I actually need. Because I've got less than what I need, that has to be the limiting reactant, and therefore this one is in excess. Or consequently, look at it this way. I've got 0.04 moles of the NaOH. If I divide that by 2, I only need 0.02 moles of the ethylene acid reacting, but I got 0.03, so I've got more moles of acid than I actually need, so therefore this is excess, yeah? Whichever way you want, but you get to the same answer. Okay, cool. That's good. All right, where are we going? I'm getting, yeah, this is some good questions. All right. Step 4, Q equals MC delta T. Okay, I'm not going to panic. I'm just not going to panic. What am I going to do? I'm going to write down my variables. What's my mass? I've got this volume of solution and this volume of solution. It tells me that the density is 1 gram per centimeter cubed. Add up your centimeters cubed. So 50 plus 30 equals 80 centimeters cubed, which is equivalent to 80 grams because of that density, okay? It tells me to use 4.2. And then delta T was 4.5. Now, remember, it doesn't matter. You don't have to change units here because a 1 degree C change in the centigrade scale is the same as a 1 Kelvin increase in the Kelvin scale. Okay, so don't do funky stuff here. So then Q equals 80 times 4.2 times 4.5. So Q equals what for maths? 80 times 4.2 times 4.5. Do we get 1512? I should don't add 273 on these questions, only on PV equals nRT. So it's 1512 joules. The 4.5 came here. So the 4.5 degree C change is a 4.5 Kelvin change as well. Okay. Now that's in joules. Now that's in joules. Okay. Now, is it exothermic? Yes, because the temperature increased. So I'm just going to put a minus sign there. And I'm also going to say that, convert that to kilojoules. So that's going to be minus 1.512 kilojoules, because I just divided that by 1,000. Okay, good. All right, what do we do next to calculate delta H? Good. Now I need to divide it by what, though? I need to work out the moles of what species? Per mole of water. Good. So delta H equals Q over N. Q equals minus 1.512 over N, which one am I going to use? I'm going to use a limiting reactant because that's 0.4. So therefore this is a 2 to 2, so that's also going to be 0.4. Where are we getting 18 from, peeps? Where's the 18 coming from? So divide that by 0.04. I get minus 37.8. Sorted. Nice. But that's a good 5 marker there. It's a good 5 marker there. 18 is the MR. Yeah. True, but remember, MK, even if your equation is wrong, they're not going to penalize you loads of times. They're not going to continue to penalize you, okay? So what I don't want you to do is, like, if you have messed one bit up, remember, they are not going to penalize you multiple times for getting one part wrong, okay? Hence, error carried forward. If you made an error once, you're not going to get punished like 4 marks in, right? Cool. Right, shall we take how long shall we have? 10 minutes? Yeah, I can go over the equation again for sure. Yeah, you can get marks with the wrong numbers. As long as, not always, but let's say you got the wrong numbers in the first part of the calculation, okay? If you got the wrong numbers in the first part of the calculation, but the rest of the calculation is correct with the initial wrong numbers, you're only going to lose, let's say it's a 5 mark, maybe 2 marks tops. So you're getting 3/5, that's 60%. Think about it that way, okay? What you can't do is get too emotional about the marks you've lost. Joshua, we're going to go till 8 if you want, okay? Equation, yeah, I can do the equation again. Okay. All right, we're going to take 10 in just a second. Okay, plus NaOH. So the NaOH is a source of OH minus, right? So the OH minus is going to react with that proton, but I need 2 lots of that because I need another OH minus to react with that proton. Okay, so I'm going to make 2 molecules of water. Do you see how that's done? And then once those are gone, the oxygens have a negative charge. The sodiums are positive, and that becomes Na plus, and that becomes Na plus. Yeah? Cool. Is 10 enough time for the people who have just done maths? Be honest, be real. No worries at all. Okay, cool. So shall we say... Let's just say 1635. It's plenty of time then, okay? You can have a half decent break, and then we're just going to keep on going with these questions. Yeah? See you soon. What do you mean? What did he say to you, S Ninja? I did not see how Neil added you, but now I am curious. What did he say? Did you deserve it? How did he find out about my bid? about your anyway, how did he find that out? And what did he say? Okay, fantastic. I'll have a look. What's wrong with Neil's beard anyway? Oh wow. What's wrong with Neil's beard though? He's got a healthy beard. What did he do? Brilliant. What A levels did I do? I did probably the wrong A levels, Romus. I did chemistry, obviously, biology, geography, and English literature, believe it or not. And then I didn't have maths that I needed to do chemistry at degree level, so I had to do maths afterwards. Yeah, I liked English lit. I liked it. It was decent. Geography was a geography was a good A level. Biology I found the hardest. Hardly. Cramming last second, that past paper, were you talking about maths or chem? Because if it's good, I'll have a look at it. Where do I get that link? Effectively, yeah, I had to do it because you need it for chem. So when you do chem, you can't, at degree level, you just can't not have A level maths. So yeah, I guess at that time there wasn't as much careers people at schools. I think you guys are really lucky with the amount of help and support you get. I mean, hopefully you get lots of support about choosing A levels correctly. Neil said, sadly, it would have been good though. Habs, have you done your English exams yet? I wish it was chalk and blackboard. The interaction between lysine and aspartic acid. Tell me more. To be fair, I teach. Just I don't really use PowerPoints much. I'm not the biggest fan of PowerPoints, but yeah. Let me see if I can find the question, so I'm not just making nonsense up. We did the color purple. We did Great Gatsby. What else did we do? Shakespeare, we did Othello, which was good. I enjoyed that. Interaction between their R groups. Nathan, try and get the actual question and I'll have a look at it. Hadi, what are your predictions for tomorrow? It's hard to predict this one because anything can come up. I actually think you are going to get some rates questions. Per Shotman, how was it? Definitely going to get some rates questions. I'll be surprised if you don't get an Arrhenius question because it didn't come up on paper 2. Yeah, I mean, I guess the aim of today is let's just try and go through all of the stuff that I've got planned. Yeah, it's just it's like it's effectively synoptic, right? So, I mean, how do you plan like? I tell you what, are there any chromatography? There isn't much chromatography, but I tell you what I can do. I've got amino acids and chromatography questions from my Easter revision course. Shall I use those? That's good. That mechanics was good. Yeah, I've got some hard MCQ questions in here actually. How many viewers we got? How many people we got in today? Did somebody say what's the predictions for England Denmark? I reckon. Where's Eflas? Yeah, I've got some NMR questions towards the end as well. So if I haven't done them by the time, just let me know. We can move on to that. I reckon 2-1 Denmark. What do you guys think? Ingerland. Do you reckon England are going to win? I'm not sure. That first match looked a bit. It's not coming home. Behave. It's not. Come on. Come on. Loads of people have the St George's flag up around here. Neil? Who calling Neil? I'm not. I'm. Why is that hating? I'm not hating. I'd like it if they win. I'd wanted Arsenal to win, but just it's realistic. And FS, who was right actually? I think you'll find I was right. Dad? You've just had an exam. I'll let you off. Why do you think Neil is an England hater? I'm not a hater. I just don't think they're. I'll tell you what it is. And do you really think they play as a team? They don't really play as a team. Just about is still right though, isn't it? Do I watch cricket? No, I do not really watch cricket. I'm Indian. No, it's great players, not a great team, I would say. Great individual players, but not a team. That's what I think. I don't know. What do I know? I don't really follow football. England, yeah, I'm with Robbo. I don't think they are. I did take a gap year, yeah. It's like watching that what's that thing on Amazon Prime? Is it the Australia England thing for cricket? No, cricket's alright. T20's alright anyway. Give you life advice. What sort of life advice would we like? What did I do in my gap year? I worked in the fracture clinic for the NHS, my local hospital. Enjoy your youth. Study hard, of course. Wait, isn't the Cricket World Cup in the States? My mum, through my mum, obviously. I mean, I was only doing I was doing admin. Should you reapply? I don't know. For us, how's it going? Cricket better than football? Yeah, football's just a bit. That England Serbia match was so dull. It was so dull. How was mechanics and stats? I heard some good things. I would say some good advice. Don't be afraid to fail. There's some good advice. Right. It's 16:35. I didn't join many at all. That's the thing. That's another sort of regret. Okay, let's go. Do I speak any languages? I suppose English counts. I mean, I barely speak that properly, but I try. I speak Punjabi badly. Badly. Define. Well, I'll let you make your own mind up on what failure is. Dav, where are you from? What do you mean by the question, Zane? I'm Indian background. I'm from London, I guess. Right. Let's go. Let's go. What are we doing? Okay. Are we ready? Thought I was Turkish. No, no, I'm Indian. Right. I think this is only a two marker. I think this is only a two marker, but it's a really good two marker. You're always going to get a question, not always, but you often get a question like this. Okay, cool. Not energy loss via conduction and convection, okay? So I think this is roughly correct, but anytime you're doing a neutralization reaction, you've got the ionic equation is this. So for neutralization, you've got H plus OH minus goes to H2O. That's it. That's all neutralization is, okay? That's it. Now, delta H neut for strong acids is roughly minus Okay, let's say it's minus 55 kilojoules per mole. But here we've got a weak acid, okay? And we're getting delta H neut to be minus 37.8. Why? Why is it more positive? I guess that's the question. Why is it more positive for a weak acid? Because it's the same reaction in a weak acid. In a weak acid, the ionic equation is the same, right? As H plus OH minus goes to H2O. So it should be minus 55, but it's not minus 55. Why not? What's happening with some of that energy? What's happened to some of that minus 55? I'll draw it out. So some of that energy which is being given out, not going to the surroundings, because if it was going to the surroundings, we'd be getting minus 55, right? But some of that energy which is being given out must be used to do what to this? It must be used to break the OH bond, because remember, it's a weak acid, so there's only partial dissociation, okay? Yeah, exactly. So it's a weak acid, so only partial dissociation. So some of those 55 units of energy which were given out are used to break the OH bond. So some energy used to break the OH bond in COOH. And that's where the 2 marks are coming from. Is everyone happy with that? Let me know if you are and we can move on. Cool. I'm going to take the silence as acceptance. Okay. Right. This is a lovely little 1 marker. Lovely little 1 marker. Do you want to have a go by yourselves with this question? Or do you want me to go through it straight away? How are we feeling? All right, I will give you 1 whole minute for this. Fire away. Okay. Put your answers in the chat, please. What are we going to do? Okay, cool. So we've got 2 gases being mixed together. Okay, cool. What do you mean just PV equals nRT, though? I mean, it is an extension of that, yeah. But think about what's happening. So we've got a flask, okay? And the volume is good question, isn't it? So you've got 130 centimeters cubed H2. That's a good question. You should be a bit confused. And you got 40 centimeters cubed of helium. So you're taking these 2. No, I didn't say it was easy. I said it's lovely. Amir, you're saying 34. Okay. I'm going to show you 2 ways to do this, okay? I don't know, is it C? So the first thing that I would do is you're taking these 2 gases, okay? You've got 2 volumes. So what could we do? Could we take the total volume? So that's going to be 170. Do we agree? Yeah? Yeah, just add them. So PV equals nRT. So I've got the pressure, I've got the total volume, I've got R, and I've got T. So what could I rearrange this for? Is your question different? Okay. Try and use these ones, please. Use these values. Gotcha. There might be a slight change in the workbook. Try and use these values if you can, please. Okay, so we're going to add those two up. I mean, the logic remains the same. Sorry, it might have just changed at the last minute. Okay, so that, if I rearrange that, that's going to give me N total. Okay, so let's just plug those in. So that's going to be 170 times 10 to the minus 6, because I could have convert from centimeters cubed to meters cubed, times 100 times 10 to the 3, all over 8.31 times 298. Okay, so let's do that, see what we get. Don't need to. Not for this MK. So we should get the number of moles, so N total equals 6.86 times 10 to the minus 3 mole. Okay, then we're adding that to this flask, okay, which was evacuated. That means vacuum, and then we're filling it up. So we're going to have to use PV equals nRT again to work out the pressure. So then P is going to be nRT centimeters cubed to meters cubed divided by 1,000,000. So then that's going to be that, okay? However, this time we're going to use the volume of the flask because that's the volume they're going to be occupying, right? Yeah, this is for 1 mark. I'll show you another way of doing it, an easy way. So we're going to use the total number of moles. This is 6.86 times 10 to the minus 3 times 8.31 times 298 all over 0.5 times 10 to the minus 3 to go from decimeters cubed to meters cubed, okay? So if you do all that, what do we get? We should get 34,000. So C. So that's one way of doing it, okay? Who would have done that? And hands up if you did get that. There is another thing that we could do. Hands if you've seen this before. Yeah, for 1 mark, I'd skip it as well, to be honest. Now, you can use this formula. P1V1 over T1 equals P2V2 over T2. Notice that T1 and T2 are the same, so these guys are going to cancel out, okay? So then you can just rearrange for P. Always put C, fair enough. But you know what P1 and V1 is, and you know what V2 is. So V2 is that. So you can just work it out like that. That's an easy way of doing it. Because P1 and V1 are exactly the same as well. Oh, no, they're not. They're different. They're different. So you're trying to work out P2. Okay, cool. So it's going to be P1 V1 over V2 to give you P2. Sorted. Okay. That is ideal gas. This is a version of the ideal gas equation. Yeah, that's a version of the ideal gas equation. Yeah. But you can do it like that. That should give you this right answer as well. So you do 100 times 10 to the 3. Yeah, the first one is way more understanding than the second one. I thought I'd show you both. You can use whichever one you like. Okay. 10 to the minus 6 divided by... Yeah, same answers. Use whichever method you like, okay? But sometimes drawing things out is really helpful as well. Okay, all right. Question 5. a bit of transition metal chemistry. Now, I'm guessing that people don't like transition metal chemistry. Would that be fair? No, Dylan, I would actually recommend doing the multiple choice last if they take long. What I would do is look at the multiple choice, and if it was like that and requires a bit more thinking, I'd just come back to it. Okay. All right. On the diagram, mark each atom that bonds to the copper 2+. Well, there is a lone pair of electrons there. There is a lone pair of electrons there. There is a lone pair of electrons here, 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 and here. Okay, so that's 1, 2, 3, 4, 5, 6. So it's a multi-dentate ligand. I've got a transition metal colors question coming up. Okay, so fear not. So multi-dentate means can form multiple coordinate bonds. Can form multiple coordinate bonds. Okay, and a ligand is what? What is the definition of a ligand? A species with? You can't do it yet. You can do it after today. A species with a lone pair of electrons that forms dative covalent bonds. Forms dative covalent bonds with metal centers, really. That will do. Dylan, I would be hesitant of that because is it always a 3D subshell? Hadia, that is correct. Cool. All right. Ooh, 3 marker. 3 marker. Is it for that one? P1 V1? Yeah. So P1 V1 over T1 equals P2 V2 over T2. If you've got a ideal gas equation where you've got P1 V1 and P2 V2, so 2 different pressures and volumes and temperatures and stuff. So remember that T1 is equal to T2, which is 298. So these guys cancel. Yeah. So this becomes P1 V1 equals P2 V2, and we're trying to find out pressure. Yeah. So then P2 equals P1 V1 over V2. Okay. So if you want to work it out, I think it was 100 kilopascals. The volume was 170 times 10 to the minus 6, and V2 was 0.5 decimeters, so that's times 10 to the minus 3. Bosh, done. And that gets you 34,000. Yeah, is that cool? All right, cool. Okay, a transition metal required practical, effectively, for 3 marks. So you've got copper 2 plus compounds are used in fungicides in vineyards. When applied, these copper ions can leach into the water supply and pose toxicity issues at high concs. Okay, cool. So we're testing the water supply near a vineyard for copper 2 plus ions, which is blue and can be formed with this EDTA ligand. The concentration of this complex can then be measured using a colorimeter. Describe the practical steps you would take to determine the concentration of the copper 2 plus in the water supply. Okay, using colorimetry. So what do we have to do first? Okay, so we're going to add, absolutely, calibration curve, super. So we're going to add copper 2 plus to EDTA and EDTA solutions. Add copper 2 plus and EDTA solutions of known concentration to produce a calibration curve. So what we're saying is we've got a low concentration of copper 2 plus, and that will be whatever color it is, and then we're going to increase the concentration, etc, 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 okay? And then what we're going to do is we know those concentrations, so we're going to plot absorbance versus concentration, and we're going to get a graph that looks like this. So these are our known solutions, okay, that we made up. Is every question on paper 3 based tomorrow on practicals? No. Some is just from general chemistry. Okay, so 1, 2, 3. So we've got our calibration curve, and then we're going to take our sample and then add EDTA to our sample, to river sample, and determine Cu2 plus concentration from calibration curve. Yep, absolutely. Lovely. Very good. Very, very good. I think we know how to do that. So shall we move on? So let's say I've got my sample. I run it in the calorimeter. So you are making a dilution series. That's effectively what we're doing. And we're going to measure the absorbance. Yeah, absolutely. Yeah, that's effectively what we've said. Yeah. And then we get an absorbance concentration plot of my dilution series effectively. I got my sample. I shine some light. So here's my sample. The transmitted light, which you get through and you measure, or absorbed. So you get an absorbance. Let's say this is my absorbance of my sample. And then on my calibration curve, I work out from there what the concentration is. We're going to do electrochemical cells as well. That's it. That was good. Okay. So let's move on. 5C. Okay, this is what we call a compleximetric titration because it's all to do with metal complexes, okay? So, let's have a look. What is the first thing that I might do here? Okay. What's the first thing that I'm going to do to actually help me? I'm going to write out a chemical equation. So my chemical equation is going to look like this. Whoop. So I've got... Nice, Dylan. So that's 2 plus. I'm adding EDTA, 4 minus. And this is making Cu EDTA. And that is going to have a 2 minus charge. Plus 6H2O. What type of reaction is this? It's not in the question, but it's revision. Actually, you won't. You'll be like, yes, glad we did it. What type of reaction is this? Is this acid base? Oh, it's ligand substitution. Nice. Why does the ligand substitution occur? What drives this? What makes this happen? Yeah, it is to do with the chelate effect, true, but let's think thermodynamically. Yes, the entropy change. What about the entropy change? We've got 2 molecules on the left. How many molecules are we getting on the right? Yep, absolutely. We've got 7 molecules on the right. Absolutely. So delta S of the system is going to be greater than 0, which is in our favor, right? Good, there's a large change in the entropy of the system, and that's going to drive this reaction because it's going to make the Gibbs energy negative. Handy. Okay, cool. Where are we going next? Do we know any values? Let's put some values underneath some species. Okay, the result was verified by titrating the water sample with EDTA, and the EDTA using the titration had a concentration of 1.5 times 10 to the minus 3. Okay, so I know the concentration. All right. Where do we go next? Where do we go next? Okay, let's put the concentrations that we know. So I've got the EDTA has a concentration of 1.5 times 10 to the minus 3. And the copper has a concentration of 8.32 times 10 to the minus 5. I'm going to put moles per decimeter cubed so I know its concentration. Okay, cool. Where are we going next? Any ideas? What am I doing next? What could I calculate? We don't know about excess just yet. Do we need an ice table? Well, let's think about this. I've got the concentration, okay? I've got the concentration. So I'm trying to calculate the volume of EDTA. That's my unknown. I'm trying to calculate the volume of EDTA. So I could work out the number of moles of what species? I've got the concentration of the copper 2+, and I know the volume of the sample. So I could work out the number of moles. Remember, N equals C times V. So, moles of Cu2+. So the moles of Cu2+ is going to be the volume of the sample, which is 30 centimeters cubed, times the concentration of the copper 2+, which is 8.32 times 10 to the minus 5. So what does that give us? How do we know all the water is substituted? We're just going to have to assume because the driving force of that reaction is going to be, I mean, that'd be pretty harsh if they did that. It'd be pretty harsh if they did that, Phoebe. Just assume that it's fully substituted. Okay, so let's work out the number of moles of that first. So 8.32 times 10 to the minus 5. So 2.496. 2.496 times 10 to the minus 6 moles of copper. Do we agree? Yeah, and the delta S of the system is going to be massively positive. So, yeah. Okay. I'm working at the moles of copper 2+. Remember, so this is the concentration of the copper 2+ in the 30 centimeter cubed sample. Okay? Does that make sense? Hi, Venki. So I'm working at the moles of copper 2+ in that 30 centimeter cube sample. Okay, so once I've worked that out, where do I go next? What's the next step in this process? So it's a 1-to-1 ratio. So what could I work out? Yeah, absolutely, molar ratio. So moles of? So the moles of EDTA, because it's 1-to-1, therefore 2.496 times 10 to the minus 6 moles. Okay, good. Then use use the moles to work out the volume of EDTA. And then finally, the volume of EDTA. How can I work out the volume of EDTA? Remember, N equals C times V. So V is going to be equal to N over C. So I've got the number of moles. It's 2.496 times 10 to the minus 6. And I've got the concentration of the EDTA, which is that. So that's going to be 1.5 times 10 to the minus 3. So my volume is going to be what? 1.664 times 10 to the minus 3. And what is that going to be in? That's going to be in decimeters cubed. So how do I go to centimeters cubed? Good. Times it by 1,000. If you times that by 1,000, you will get 1.664 centimeters cubed. Whew. How was that? Why did the product have a 2- charge? Okay, so the copper 2+ has a 2+ charge, and the EDTA, when it bonds to it, has a 4- charge. So +2 take away 4 gives me -2. Yeah? Okay, let's continue. Oh wait, we've got a bit more on this question that I haven't answered. So, why is it? So will this give us accurate results? What do you guys think? I will say it does not give us accurate results because it's a really small volume. 1.664. Will you get no marks if you get the equation wrong? Not so much no marks, but it's gonna make it harder to get it right, if that makes sense. I mean, you'll lose 1 mark if you get the equation wrong, but also, I guess if they use error carried forward, it will help you there, if the rest of it is correct. Does it say in centimeters cubed? No, it doesn't say in centimeters cubed, but if it says to put it in centimeters cubed, do it in centimeters cubed, just in case, okay? Because we normally use centimeters cubed. Okay, so I'm going to say that's a really small volume, so it's not going to be accurate. Small volume, so not accurate. Okay. Small volume means a large percentage error. Good. Okay, so how could we reduce the percentage error? There's 2 things that we could do. What 2 things could we do? That's pretty concentrated. Oh, large volume of what? You could use a large volume on one thing. All right, we've got to be specific. You can't just say these terms. You've got to specify what that is for. Larger volume of water. Absolutely. Larger volume of river water, right? So yeah, or higher concentration of copper. Is that what you said? Yeah, higher concentration of copper. And the way that you get a higher concentration of copper is by using a large volume of water, right? Because you're going to have more moles of copper. So use larger volume of river water or sample. What else? There's one other thing that we can do to the EDTA actually. How can we get a larger volume? I'll go through that again, Hadia, in just a second. What could we do to get a larger volume of the EDTA? Think back to what I said. What could we do to this denominator? Yes, lower the concentration of EDTA. Because if you dilute it, with making a lower concentration, we're dividing by a smaller number, we're going to get a larger volume, right? So, third point is, I mean, you don't have to say the third point, just one of those would do. You dilute the EDTA concentration. Okay, why are we talking about this? Because percentage uncertainty is the uncertainty of the measurement divided by the value of the measurement. Okay? Times 100. Well, let's say that's just 0.1 for argument's sake. If the value of the measurement was, I don't know, 1.6 versus 50.6. Which one's going to give us? Where I didn't plan any for this, but I'll do some Arrhenius questions in the break. I'll just easily chop those in. Which one's going to give us the lowest percentage uncertainty? It's going to be the one where we divide by a bigger number, right? So the larger the volume here in this case, the smaller the percentage uncertainty. Does that make sense? Right, how are we doing? You got to take it in turn. There's no like hard and fast rule. You got to look at the question specifically. Yeah, there's Hess in this for sure. Okay, titration curves. How are we feeling about this? Okay. Shall we continue with 6 and then have a short break? Okay. Ooh, 8 to 10? I'm not sure I agree with you. Let's have a look. So there's 7. So we're looking for the vertical section, right? Because the vertical section is where that's what the equivalence point is. That's where the indicator is going to start to change color. So I'd say roughly 7.2 to 10. Actually, no, 7 is probably fine. Actually, 7 to 10. Even 10.2 actually. Yeah, I would go from 7 to 10.2 max. 7 to 10.2 max. Can't be 6. Okay, so you don't. I mean, you're probably going to get a data booklet, Dylan, which can give you pKind anyway. But you want your indicator to change color in that vertical section here. Okay. Indicator to change color within the equivalence point. So it has to be in that vertical section. Just put your ruler on the line and see when it stops being straight. Yeah, exactly. So this vertical section, that's your equivalence region there. There we go. That bit. You want your indicator to change then, because at the equivalence point, that tells you when to stop. pH is always to 2 decimal places. pH equals pKa, not kPa, pKa at half the equivalence point. In fact, we've got a question on that now. Right. What is the expression for Ka of Hx? Okay, cool. So because I'm not very bright and I can't remember what it was, I'm just going to write down that Hx dissociates to H plus and X minus. So I'm going to write Ka from scratch. So Ka is going to be H plus X minus all over Hx. So that's just 1 mark for writing Ka. It's true, S Ninja. Right. Determine the concentration of Hx in the initial solution. Okay, so what are we actually doing? So for the original solution. Okay, so how do we get that concentration? So we're doing a reaction, aren't we, with sodium hydroxide? Okay, so, okay, I understand. Right, how would we approach this? For 2 marks, actually requires a bit of thinking. What are we going to do? I'll explain what's going on. No, the point is that one didn't come to me straight away, okay? So I'm actually just drawing this out to actually say that, oh, this is how we're going to work it out. Equation then mole ratio? Yeah, okay. So what's in here first? What's in the conical flask if we're doing this titration, if we're looking at the pH? We've got the HX in there, right? We've got the HX in there. So we've got a burette. And we've got NaOH, and that's going in to the HX. Is everyone happy with that? So what do we have to do? What happens at that point there exactly? At that point there, what actually happens? What effect? What phenomenon, I should say? When the number of moles of NaOH and HX are equivalent. That's when the neutralization occurs. Exactly. So we are going to get NaX plus H2O. And that is going to tell us, the concentration of HX that we had in the flask initially, okay? So what volume does that equate to? Is that 24? Yep, so 1, the volume of NaOH. Yeah, that's at the equivalence point, exactly. So the volume of NaOH at that point is 24. Convert to decimeters cubed, times it by the concentration. And the concentration is 0.1. So that gives me 2.4 times 10 to the minus 3 moles of NaOH. Okay, so I've got the number of moles here. So how do I work out the moles of HX? It's a 1-to-1 ratio. Therefore, 2.4 times 10 to the minus 3 moles of HX. Is everyone with me so far? That's the number of moles of HX in here. And I worked that out from the titration. And then step number 3, what do? I'm trying to work out the concentration. And remember, concentration is the number of moles divided by the volume. I've got the moles. Do I have the volume? Yeah, here's my volume. It's 25 over 1,000. So my concentration equals, yeah, good. Is it 0.096? Yay, nay? I think that's right. Hey, Mohammed, how's it going? Good. So the working out's on the other page, but it's 0.096. But for 2 marks, that, requires a bit of thinking. And if, at that point, you're not in that flow to spend a bit more time on it, come back to that question later. Okay. All right. Question D. Compute the pH of the HX solution before adding any sodium hydroxide. It's predominantly 1-to-1, but take every question in turn. Don't go in there with hard and fast rules, because if the rule's broken, then you can throw you, right? Okay. So compute the pH of the HX solution before adding any sodium hydroxide. Okay, so basically this is saying what? Determine the pH of a weak acid. How do you determine the pH of a weak acid? Okay. Yep, good. So, first thing we're going to do is just rewrite Ka. Nice, Nancy. Good. Okay. So, at equilibrium, I'll redraw the chemical equation. So you've got HX. Yes, exactly, Phoebe. Yeah, good. Now, what can we say about the number of moles or the concentration of H plus and X minus at equilibrium when this thing dissociates? That these guys are effectively the what? They are roughly equal. Okay? And if they are roughly equal, we can simplify this to what? H plus squared over HX. Yep, exactly. Good. Now, we know Ka and we know HX. So, multiply through by HX. So this becomes Ka times HX concentration equals H plus squared. So take square roots of both sides. Bosh. Now plug in your numbers. What was Ka? 2.62. 2.62 times 10 to the minus 5? He says, I can't remember. And then 0.096. And that gives me H plus. Let's have a look. 2.62 to the minus 5 times 0.096. Square root of that. And that gives me 1.59 times 10 to the minus 3 moles per decimeter cubed. So pH equals the negative log of that. So pH equals 2.80. Done. Lovely. Okay. Question E, 1 mark. And there were a lot of questions on this in the chat. What do we do? That's a 2 marker actually. 2 marks. And this one's a 1 mark. So they're being quite stingy here. So let's have a look at E. Right, should we have completed this graph? Okay, I wonder if the order is correct. Okay. Okay, so what do we do on the graph then? It's really hard to see. But what are we saying on this graph? Wait, are England winning? Hello? Wait, are England winning? I've got no idea. Oh. Okay. Okay. So England are winning. All right. Where were we? I've totally forgotten. Okay, so what I'm going to do is start plotting this graph. I'm actually going to do the next question. All right. So at 0, everyone's like getting pumped. So at 0, before any NaOH is added, I had a pH of 2.8 if I'm not mistaken. Yeah, 2.8 if I'm not mistaken. Okay. Fine. So 2.8 is here. Do we agree? 2.8 is there? Okay. Then what? All right. Also, I actually don't need to because I've got Ka. So at half the neutralization point, pH equals pKa. I know Ka is 2.62 times 10 to the minus 5. So to work out pKa, the negative log of that, 2.62 exp to the minus 5. So I get 4. So pKa equals 4.58. Everyone happy with that? And that's at 12 centimeters cubed of NaOH addition. Okay, cool. So then going back to the graph. So at 12, somewhere here, there's 11, there's 12, 2, 4, 6, something like that. Okay, and what's going to happen is this graph is going to go up first. And then it's going to flatten out in the self-buffering region. And I know I'm talking to myself because Eagling matches on. And there you go. Something like that, okay? Why is the pH equal to kPa? Okay. Is anyone here or am I talking to myself? All right. Wicked. Okay, cool. Right. At half the neutralization volume, okay. No, I know. No, you guys are doing amazing to even be here, really. Right. At half the neutralization point, we can say that HA equals the concentration of A minus. If I go back to this, so HA, H plus A minus, and I'm going to write my expression for Ka, and that's going to be H plus A minus all over HA. So if that is true at half the neutralization point. Oh, Aisha, this is how I'm... Leo, yes, you do. No, I like this stuff. This is good. Right, so at half the neutralization point, take my word for it that this is true. Okay? This is just true. If this is true, how does this expression for Ka change? A minus and the HA cancel out, right? So we're left with Ka is equal to H plus. So if I take a negative log of this, and I take a negative log of this, the negative log of Ka is pKa, and the negative log of H plus is pH. And there you go, bosh. So that's why at half the neutralization point, that occurs. So you can simply say pH equals pKa, and Bob's your uncle. Yeah, that's it. That's why. I mean, take my word for this bit. It just is. This is for question. That is only true at half the neutralization point, Phoebe. Correct. Okay. Why do we increase the volume but can't increase the volume? So for question 5, why do we increase the volume but can't increase the volume for the percentage of change in temperature? It's okay. So Iramide, good question. It's just it was a different question, right? So imagine you've got a river sample here. And you have this many copper 2 plus. So the final answer to E was 4.58. To get more, let's say I increase the volume of the river sample. If I increase the volume of the river sample, are there going to be more copper particles in there? I guess that's the difference, right? I guess you've got to be really specific because we know that we're changing the volume to get more copper 2 plus ions in that river water sample. If I've just got whatever there was, I don't know, HCl of concentration 0.1, and let's say I used 10 centimeters cubed. Okay, let's say I use a larger volume. But my concentration remains the same. It's actually, in fact, let's say I use a larger volume, my concentration changes. It's not being very specific is what we're saying there. So you've got to say the concentration changes. You could have guessed, I guess you could have said reduce the volume. But if you reduce, yeah, it just you've got to talk about concentration for the other one because we're talking about the HCl and the NaOH particles there. Yeah? I guess in this one you could have said use higher concentration of copper 2 plus. But the only way that you achieve that is by having a larger volume of river sample. Does that make sense? I hope it does. So you can't always have the same stock reply for the same. Yeah, I mean, you can use Hadia's advice there. But you can't just use a stock response and hoping that you're going to get the marks. You've got to tweak it to what's actually happening in the practical. Yeah? I guess if in doubt, say concentration as a get out of free card, yeah? Okay, shall we have a short break? How long? 10? Anyone there? Yeah, I'm happy to carry on. Shall we carry on? Okay. All right, let's carry on. No, please break. I'll tell you what, let's carry on a bit, and then if you need a break, take a break and just come back at your own time. Whoa, Dylan Green. Explain the function of anti-bumping granules during the reflux process. Yeah, let's take 5. Let's take 5 because I think people are struggling a bit today. Yeah, it stops large bubbles forming, nucleation sites for bubbles, all that jazz. Yeah, it doesn't reduce bubbling, stops large bubbles forming, okay? All right, let's take 5. We'll come back at 17:35. Hey, we're going to go on for a bit, so don't worry. Take 5, grab a coffee. Catch you in a sec. Hello, how are we doing? Okay, right. Question 7. I think we've done that. Okay, 7B. Let's go. Question 6 is a nice question. I like that. Do we need to do 7B or have we done enough calculations? Let me know. Hello? I mean, it's 2 marks. You've got to show that they're... All right, let's do it. Let's do it. Let's do it. All right, cool. So we've got excess sodium hydroxide. We've got to show that it's excess sodium hydroxide. Okay, so we've got ethyl benzoate. Yeah, exactly. It's the same as all the others. But let's do it. We've got 6.5 centimeters cubed. I'll do this one quickly. So rho equals m over v. So the mass is equal to rho times v. Right, so that's going to be 6.5 centimeters cubed times 1.08. Okay, cool. That gives me 6.534. Or have I done that correctly? 6.5 times 1.08, 7.02. There we go. 7.02 grams. Okay, that is the mass of that. So now I need to work out the moles. So I'm going to divide that by 150, and that's going to give me 0.0468 of that. Okay, cool. Phoebe, you were correct. It is 7.02. Okay, and I've got 32 centimeters cubed times 2.2, which is a conch. So 32 over 1,000 times 2.2 gives me 0.0704 moles of that. Cool. So we've shown that there was an excess of sodium hydroxide used, okay? Excess. Everyone happy with that? Cool. Yay? Right, what do we do next? Why did we use an excess? Sorry. Why did we use an excess of the sodium hydroxide? Well, we use an excess to make sure what? I always say to allow for... Okay, let's have a look at what's actually reacting. But let's be specific, okay? So we're using an excess of this guy. So this is an excess and this is the limiting reactant. We always use an excess of something to make sure the other reactant fully reacts. So to make sure all of the ester reacts, okay? That's it. To make sure all of the ester react. That's it. Okay, D, explain why an electric heater is preferred over a Bunsen burner for this hydrolysis. Well, one of those things is flammable. What's flammable? Yeah? Something is flammable. What is flammable? The ethanol is flammable. The NOH is not flammable, but the ethanol is flammable. Okay? Right. Describe the purpose of reflux in the hydrolysis process. You've got to be really specific with your words here, okay? Why do we use reflux? So that the something vapor returns to the flask. Yes, you have to say reactants, okay? So that the reactant vapor returns to the flask and reacts. Do not say products, you will not get the marks. It's all about making sure you get maximum conversion of the reactants. Okay. Nice questions, just 1 and 2 markers. How does it actually do that? Because we don't use a bung. We don't use a bung, but we have a condenser, right? I'm just doing a section of it, but imagine here is a condenser here. So it's cold, it's covered with water. So imagine this is a gas. So it's jiggling around, and when it hits the cold surface, what's going to happen to that jiggle? It's not going to speed up, is it? Because it's going to transfer the heat to the cold thing. And as it slows down, these guys are going to actually coalesce, come together and form a liquid. And when it forms a liquid, it trickles back down into the pot. Does that make sense? Okay, write a balanced equation for the reaction between sodium benzoate and hydrochloric acid. Okay, so this is hydrolysis of a salt. Okay, cool. So C6H5, COONA, which is sodium benzoate. Okay, plus HCl. What are we going to get? What are we going to get? So those guys are going to swap. So we're going to get C6H5 COOH plus NaCl. Okay, so this is the sodium salt of an ester. And to convert the sodium salt of an ester to an acid, we just use an acid. It will no way ever form an acyl chloride, never. So sodium salt of ester to acid, carboxylic acid. It will not form an acyl chloride. There is a way that you can go from a carboxylic acid to an acyl chloride, but you don't need to know it for AQA. But the way you do that is PCl5 or Socl2. Okay, discuss why sodium benzoate dissolves in cold water while benzoic acid does not. Right, what are we saying? Good question. Don't know if you get the marks for saying polar. You get the marks for saying polar. Let's have a quick little look-see. You have to say one word. Yeah, sodium benzoate is ionic, right? Sodium benzoate is ionic. You have to say that word. I think if you say polar, you don't get the marks. So sodium benzoate is ionic. Sodium benzoate is ionic. Okay, but I could argue that if you've got benzoic acid, which looks like this, you've got an OH group. Surely that can hydrogen bond with water, can't it? Don't you think? Surely benzoic acid should be soluble in cold water because this bit is polar. Why though? That's polar, surely. Why does it not? Because because the aryl group, or the C6H5 group, is non-polar. Absolutely. The C6H5 group is non-polar, despite there being a polar COH group, okay? So the non-polar C6H5 group despite there being a polar COH group. And that offsets that polarity there. Well, I mean, we're going on a bit of a tangent here, but what is solubility all to do with? Ah, yeah, so in warmer water, it might dissolve, right? So it's all to do with the breaking of the bonds in the molecule and forming new bonds with the solvent. So it's going to be a trade-up between the two. So in cold water, that doesn't happen. Okay? And that big non-polar group, yeah, it can form some hydrogen bonds with water, but that bit can't form hydrogen bonds with water, and that's not going to mix with water. So there's going to be a trade-off there. Okay? Right. Hey, 6 marks. We did this last time, paper 2. We should know what to write here. What are we saying? How are we going to purify the benzoic acid? This is the minimum volume of hot solvent, okay? So first, so dissolve in the minimum volume of hot. Okay, it doesn't ask for it, but of course that's fine. So it doesn't ask for it, but why are we doing that? To dissolve the product and impurities. Okay, what are we doing next? Yeah, we're filtering to remove the impurities. How are we filtering though? We're filtering cold or hot? We're going to do a hot filtration, so you hot filter to remove any insoluble impurities. Okay, once we've hot filtered, what are we doing? Yeah, fluted filter paper, they could say. Yeah, we're going to cool to recrystallize. Nice. We're using hot because things are more soluble in if the temperature's hotter. And then what are we doing? Number 4, we're going to filter and reduce pressure. Yeah, vacuum filtration. So filter under reduced pressure using a Buchner funnel to speed up process. Cool. Step number 5, what we're going to do once we've got our solid? Wash with cold solvent and dry. Excellent. Wash with cold solvent and dry. Absolutely. We're washing it with cold solvent to remove soluble impurities. To remove soluble impurities, you want to use cold. You don't want to heat it up and, actually remove some of your crude product that you spent time making. Yeah, it's a version of it. It's similar to the aspirin crack. Absolutely. Cool. We are getting there. We're getting there. We're getting there. Okay, cool. Right. So the specific marking points would be, I will go back. You have to say hot solvent, dissolve in hot solvent, okay? Have to say that. You have to say minimum volume. Second mark. You have to say filter hot. Then you have to say cool to recrystallize. And then you have to say filter and reduce pressure. You can say with a Buchner funnel. And then wash with cold solvent and dry. That's where all the marking points are coming from. No, it's good. It's good to know where they're coming from. Yes, we are getting a saturated solution of the crude product. That's why it's minimum. But it dissolves the product and the impurities. Hopefully. But what happens is we cool to recrystallize because we've got a saturated solution. Because we've got a saturated solution of the crude product crystallizes. Solvent is calm without a named example, correct. So we get the cool crude product crystallizing, but the impurities, they remain dissolved because they're not saturated, Sonma. Yeah? Okay, cool. Right, where are we? We got another percentage yield question, have we? Blimey. Okay, cool. I mean, I'm guessing this is going to come up, these percentage yield questions, right? So make sure we're going through them. Okay, let's have a look. So what are we going to do first of all? So theoretical yield, I guess. So the theoretical yield is going to be the moles of ethyl benzoate times the MR. So the moles of ethyl benzoate was 0.045 and the MR is 122, I think. So what does that give us? 5.49 grams. Okay, cool. So to work out the percentage yield, you sure? 150? Let's have a look. It could well be 150. All right, 150 it is. Okay. No, I'm probably wrong. Let's try and do that my 150. We'll go with 150. No. Let's use a question. So 0.045 times 150 gives us 6.75. Will I be able to send a difficult question through? Yeah, I'm happy to do that. Yeah. So percentage yield equals 6.75. No, 5.3 over 6.75. Apologies. 5.3 over 6.75 times 100. Okay. 78.5? Okay. Yeah, I thought it was. Hang on. Yeah, exactly. I was right. Thought I was right because this is asking for. Because we've got to do it for benzoic acid. Right? I'll draw out the. I think I was right. I got thrown. No, I was right. Okay, I'll redo it. I'll do it properly. I was going fast. Okay, the 150 was for the ethyl benzoate. Okay, so let's just go back to see what we're making. Okay. So we're trying to make benzoic acid from ethyl benzoate. Okay. So ethyl benzoate, let's do a little equation. Ethyl benzoate to benzoic acid. We were just got tricked. Yeah, well, Mohammed, he knows. Thank you there. Right. So we had the moles of this is going to be 0.045, and then I need to use the molar mass of benzoic acid. Right. So benzoic acid is 122, if I'm not mistaken. Am I right there? So C6H5COOH. 12 times 6 plus 5 plus 12 plus 32 plus 1. Yeah, 122. So I was right. Because benzoic acid has an MR of 122. That has an MR of 122. Yeah, that's the MR of the benzoic acid. Remember, if you read the question, we're trying to calculate the percentage yield of benzoic acid, right? If you use 150, you're using the wrong MR. Because 150 is the MR of that, not the target compound. Okay, so it's 122. I've done it. So then what we're going to do is work out the mass of benzoic acid. Theoretically. So the mass of benzoic acid theoretically is going to be 0.045 times 122, which I did ages ago. Right. Yeah, 5.49. And we obtained 5.3, so the percentage yield equals 5.30 over 5.49 times 100. It's going to be high. Is it around 90 something? 96.5? That's high. Okay. Aisha, yeah, it is. And it is a 1-to-1 there. It is. So, yeah, fair assumption. Yeah, absolutely. So why do we not get, if you use moles, absolutely fine, I understand. Yep, you can use the mole percentage yield or the mass percentage yield. Would they escape? I think, say, losses on transfer. So, can't say loss to surroundings, but I get what you mean though. But when you're transferring due to lots of steps, you might lose some of your product, okay? Kasifi, yep, I can have a look. So, loss of product during transfer. Yeah, exactly. So lots of product during transfer, some left in containers. I will give you some left in containers, so not transferred. Absolutely. Good. All product not dissolved in solvent. Don't know if impurities present might actually take it up a bit though, mightn't it? I guess that what I'm saying is, let's say it's that high, close to 100%, or even sometimes greater than 100%, your product might be wet. So impurities, which water is an impurity there, I guess, it might take the percentage yield up, if you see what I mean. Yeah, so a lot of these are going to be incomplete reaction or losses on transfer. That's pretty much it. Either you dropped some because you were being clumsy, or you might, oh, look at this thing. Yeah, exactly. Mohammed drank some. Exactly. Some got left in the container. What do you mean loss on isolation, though? Yeah, okay, no, I see what you mean. When you're trying to isolate the product, you got some loss. Yeah, I'll give you that. That is valid. Fair. Fair point. Okay. Should we take 5? Just want to get a water and come back. I'm happy to go to... No, loss and isolation is valid for sure. Question 8's nice question as well. We should blitz through the next bit, actually. Do you want me to go to 8? Could go to 9. Should we go to 9? Don't know. Let me know if you want me to go to 9. I just need a short break and then I'm going to come back. Yeah, we're gonna go on. We're gonna go on. All right, give me a sec. You last till however long you need to last till. Go till 12. Get the results. That's what I want. No, no, last till however long you need to last till, and then I'll go on till 9. We'll see how we go, okay? I'm just gonna grab a snack. I'm gonna make a cup of tea as well. All right, catch you in a bit. Come on, no chance. Okay, fair enough. See how specific you are with the units. I will go to 2100. No ambiguity. Catch you shortly. You need exactly. We've done fair few 6 markers. Done a fair few 6 markers, and this is a cheeky question. That's a cheeky question, number 8. All right, I'm gonna come back in a sec. That is a really good question. You've got to see whether uni's for you. That's all I'm gonna say. That's a big decision. I can't decide that for you. But you know, apprenticeships are fantastic. You learn whilst you're doing it. You can get degree apprenticeships as well. You know, once you get to it, you'll be earning from the start as well. So there's lots to say for them. Uni is uni is basically free. Kind of. You're not wrong for a shot one. Right. What's your favorite coffee? I've just made I made a cup of tea. I've got a cold coffee there as well. I do like a mocha. I'm partial to a mocha, can't lie. But I normally just like flat white. Should I drink the cold coffee? Oh, I don't know, you know. Right. It's like a iced coffee. It's not bad, actually. All right. We good? So we do question 8? Let's go. I was Manny's boss for ages. How was he? Anyway, we didn't come here to talk about Manny. I don't know why I'm asking. Right, question 8a. Draw the displayed formula of a straight chain positional isomer of pentan 2-ol. When dehydrated, results in a single alkene. You neglected your AQA. I'll have words. Shall I talk to him? Okay. Ooh, good question. Right. Straight chain. That's a big clue. What do you reckon? It's asking for a straight chain positional isomer of pentan 2-ol. So, if I draw pentan 2-ol, then give you the question. So, 1, 2, 3, 4, 5. So this is pentan 2-ol, okay? Right. And we're looking for a straight chain position isomer that when dehydrated gives us a single alkene. Okay, well let's have a look. I know it's asking for displayed, but just bear with me. So, if we dehydrate this, does this give us one single alkene? And the answer is yes. Okay, are we happy with the dehydration mechanism or not? You can't put the OH here because that will give you a mixture of alkenes, and I'll show you why. My green screen is breaking, is it? Oh, it is, isn't it? Blimey, it's the wind. It's all right. Okay, cool. I don't know what to say about that. Right, which way is it breaking? To the left? Let's have a look. I'll sort that out. All right, I'll go through. It's this way. All right. Hang on. Is that better? Okay. Right, so let's do dehydration mechanisms, okay? You don't really need to know them, but they're helpful to answer sorts of questions like this, okay? Okay. 1, 2, 3, 4, 5. Okay, so here is pentan 2-ol. So let's say I go to pentan 3-ol. This is pentan 3-ol. Pretty sure I'm on to answer your question. I've mostly done it at Excel, but I've done AQA as well and OCR. Okay, so dehydration is removal of this. So we protonate this to make it a better leaving group. That breaks. And what can happen is that's your alpha carbon, okay? The reason that's your alpha carbon is because that contains the COH bond. That's why we call it the alpha, okay? Now, what you need to do is look at the betas. That's a beta carbon, and that's also a beta carbon. So when that breaks, one of the beta hydrogens on the beta carbon is going to break off, but it can break off there, and it can break off there. And that's going to give you a mixture of alkenes. In fact, no, it's not going to give you a mixture of alkenes, but it's not going to be straight chain, okay? So that won't work. Does that logic make sense? So it can't be on position number 3. Well, if it can't be on position number 3, where else could it be? The only place it could be is on position number 1. So let's put it on position number 1. We need an acid catalyst for this. So the acid catalyst, we protonate this, and I'm going to go through the mechanism. Can I just put C4H9 there? In fact, that doesn't help. I'll draw it all out. I won't be lazy. 1, 2, 3, 4, 5. Okay, so we protonate that. That becomes OH2 plus. Okay, what did we call the carbon that contains the OH bond? Is it the alpha or the beta? These are labels that are helpful when we're doing questions. So that's the alpha carbon. That breaks. Well, if that leaves, look at the beta. We've only got the beta in one position, right? And what's going to happen is this CH bond is going to break and form a double bond. Done. So we're going to get this. Sorted. And that becomes an H here. And then what are we left with? C3H7 at the top. That's the answer. So it has to be pentan 1-ol. This is pentan 1-ol because pentan 1-ol is a straight chain position isomer of pentan 2-ol. Does that make sense? So this is 1, 2, 3, 4, 5. So that is the correct answer. Does that make sense? So let's just see if we were satisfied what the... Yes, it wasn't asking for the alkene bit. It wasn't asking for the alkene bit, but I've done the alkene bit for you anyway, just to show you. But it's asking for a straight chain position isomer of pentan 2-ol. So this is straight chain. That when dehydrated gives you only one alkene, and we can only get a single product from the dehydration of pentan 1-ol, which satisfies what the examiner is asking for. So we're done. Okay. B. As for one measly mark, draw the skeletal formula of a chain isomer of pentan 2-ol. Yeah, that won't work because it will be a branched one, S-Ninja, but you see why now, hopefully. So draw the skeletal formula of a chain isomer, so we're looking for branches here, of pentan 2-ol that upon dehydration forms a variety of alkenes. Okay, what do we think? Pentan 3-ol will not work, Jazz. Why not? Because pentan 3-ol is not a chain isomer. Pentan 3-ol would be a position isomer. Okay, so that ain't going to work. So the key word there being chain isomer. So let's... Absolutely. So Elsbell's, I think, question is, do we need to make it branched? Absolutely, because that's what chain means, okay? That's the definition. Okay? Right. 2-methyl-butan-2-ol. All right, let's have a look at that. 2-methyl-butan-2-ol. All right, I'll do displayed first. So butan is that. So we're saying 2 methyl group there, there. That's going to be that. Yeah, that might work. That might work. And let's have a look at Phoebe's as well, because let's have a look if this works, okay? What is my technique to figure out if this works? I'm going to find my alpha. I'm just going to get rid of that. I know I haven't really... I'll protonate it with an acid catalyst, so there you go. Well, I can get a double bond forming there, but I've got a beta on that side as well. I can also get a double bond forming there. So will that give a variety of alkenes? Yes, it will. So that would work for sure. And let's have a look at what Phoebe said. So you are saying 3-methyl butan 2-ol. Okay, let's have a look. Okay, 3-methyl is there. Okay, would that work? 1, 2, 3. That would work as well. That would work as well, because let's protonate that. That becomes a plus. That moves. Check your betas on either side. Do we have hydrogens on the beta carbons? Yep. Would we get a mixture of products? Yes, we would. So well done, everyone. Good work. Really good work. Okay. Why would I not get the marks for this? I haven't drawn it skeletal, okay? So let's draw it skeletal. 1, 2, 3, 4. So there's my 4. So that's that one. And then 1, 2, 3, 4. Sorted. Well done. That was a good question. Impressed. Impressed. And it's only 1 mark, but that's proper chemistry and that's showing understanding. So you guys are doing well. Okay. 8C. Draw the structure of an unbranched functional group isomer of pentan 2-ol. What's the functional group isomer of an alcohol? It's not an aldehyde. Not a ketone. Not a cyclo. OH is the same. It is an ether, Sonma. Well done. Correct. And Hadia, well done. It is an ether. Okay, cool. So, pentan 2-ol. Right, so let's just draw this out. So, pentan 2-ol. C5 H11OH. Does that work? I think. Yeah. Let's double check. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, perfect. Okay, so that is the formula. So we've got C5 H12O. That's how many carbons, hydrogens, and oxygens we have. So if we're going to make an ether out of that, we're trying to make an unbranched functional isomer. Okay, an ether is like this. So you've got an O single bond C. This is an ether. So this would be dimethyl ether. But the main thing to see here is that, look, if you've got C2H6 and 1O, and if you have an alcohol, do you have the same number of carbon, hydrogen, and oxygen? Yes. Is that also C2H6O? Yeah, it is. So you can see that they've got the same formula, but they've got different functional groups, and that's what a functional group isomer is. Like, but they do not have to have the same numbers of CH3s on either side. Not at all. Okay, so it's 3 on one side, 2 on the other. That's it. So let's put that on one side. CH2, CH2, CH3. CH2, CH3. Does that add up to C5H12O? 1, 2, 3, 4, 5. We've got 5 carbons. 3, 5, 7, 9, 10, 11, 12. 12 hydrogens, 1 oxygen. Done. Okay. Yeah, so an ether is, yes, and the O is bonded to carbons as well, okay? All right. Aldehydes and ketones are functional group isomers. You should know that one as well. Trying to think. I'll go through them when I'm in the headspace to actually think about it. What other stuff should we know? Let's just work it out, actually. Are these functional group isomers? So that's ethanol and hang on. Yeah, so aldehydes and ketones are functional group isomers that you should know. What else? Is carboxylic acids are not. But carboxylic acids and esters? Would that work? So here is an ester. No. So carboxylic acids will not work. Okay, cool. So the other one I would say is aldehydes and ketones is one to remember, okay? Aldehydes and ketones, alcohols and ethers for sure. All right. Question D. This is another measly one marker, but shows a lot of understanding and sort of logic if you can work this out. So we're looking for an isomer of pentanetol that is an alcohol but doesn't undergo dehydration when treated with conchosulfuric acid. What are we really saying here? It's not cyclo, trust me, because why did I bother going through all that alpha beta nonsense? It wasn't to try and make this harder, but what is a requirement for dehydration? It's not a tertiary alcohol, actually, no. Because let's work it out. Here is it's not a tertiary alcohol. Nope. That isn't the requirement necessarily. I see where your logic is. It's close. Okay. On my alpha, I can have hydrogens. However, there's my alpha carbon, there's my beta carbon. In order for dehydration not to occur, what can I not have on, but it's asking for an isomer of pentanetol that doesn't undergo dehydration. Pentan 1-ol undergoes dehydration. So my beta carbon cannot have any hydrogens directly connected to it, right? I think that's what Jazz is saying. Absolutely, Jazz, correct. So this, we can have no hydrogens here. So if we can't have any hydrogens there, let's put some alkyl groups, some methyl groups. Okay, so what do you think is going to be on, what's remaining on the alpha carbon? It has to be some hydrogens. The alpha carbon is the one where the COH bond is. So this is my alpha carbon. My beta one is the one next to it, okay? And a requirement for dehydration is the beta carbon must, so the beta carbon must contain, or the adjacent carbon, if you want to look at it that way, must contain a CH bond, direct. This doesn't contain a CH bond, so no CH bond here, no CH bond here, and no CH bond there, okay? Does that make sense? So let's number this. So 1, 2, 3. Amazing. Okay, so if we are numbering this, the longest carbon chain is propan 1-ol, and this is going to be 2,2-dimethyl. Yeah, don't discount it's going to be 2,2-dimethyl because this is the longest carbon chain from here. And then these two are both on the second carbon, okay? Do you know what? S Ninja's got a good point. Don't discount those one markers. When you're practicing, those one markers really do make you think, okay? Oh, hang on. You know, I've been going through that dehydration mechanism. Well, look, you don't have to know it fully, but you should be able to apply your logic as to what happens. So for 3 marks, you have to draw 2 curly arrows. Right in the chat, what do we have to do? OH2 plus to C, you sure? If you drew a tertiary alcohol here, Jazz, you would be wrong. Yeah, that is not correct. Because this isn't a tertiary alcohol, right? This is a primary alcohol. What was the name of the isomer? That was 2,2-dimethyl propan 1-ol. One from bond to the OH2 plus. Good. So this COH2 plus bond breaks, okay? Because that is a good leaving group, so we generate water now. We have to make it a good leaving group by giving it a little nudge to go away. Okay, what happens next? Well, look, that's my alpha. I don't have a carbon adjacent in that direction, but if I go in this direction, do I have an adjacent carbon with a hydrogen bond? Yes, and that CH bond is going to break and form that double bond. Sorted. Lovely. That's it. What is the name of the mechanism? Well, it's not dehydration because it tells you it's dehydration. So what are we doing? We are getting rid of something. If you want to look at it that way, yeah. Do you have to show ion pairs? Yeah, it's elimination. What do you mean, do you have to show ion electron pairs? Oh, do you have to show lone pairs? No, because the lone pair was given here. But normally you should show the lone pairs. Yeah, but the lone pair was shown in the diagram anyway, so fair. Okay. The last one for 1 mark, but it's a good question again. An isomer of the final product can also be formed in the reaction described in part E. Okay. So this is the final product. This is what we're looking at, okay? Illustrate the structure of this isomer. All right, what are we saying then? Aha, okay. I see, I see. What do you think? Now, nice. Okay, so I'll redraw this. Very good, very good. Okay, well, on this side, it doesn't go on that side. It goes on this side because I was a bit misleading because there is a beta hydrogen there. There is a beta hydrogen there, okay? So, let's have a look at what happens. I'll draw it properly so you can see it. Have you guys done this in school? I'm curious. So that breaks off. Awesome, good. So the alpha, okay, I'll highlight it. So find your alpha carbon. That's the one where there's the COH bond. That's the alpha, okay? So the beta is it is dehydration, but it tells you it's dehydration, so it's elimination. Now, have a look next to it, adjacent. So these are just labels we use. You could call them Dave and Bob if you want, but I'm going to call it alpha and beta because those are the labels we use. So the alpha by convention is the one where the COH bond is, or a carbon halogen bond. Go to the left of it, go adjacent, next door. This is your next door neighbor. And is there a CH directly attached? Yes, that's a beta, but we've already done that in the first bit, okay? However, let's go this direction. If we go in this direction, we've got a CH3, right? Well, on this next door neighbor, do I also have a CH bond directly attached? Yes or no? Once you draw it out like that. The answer is yes. So we've looked at this beta carbon. We've done that one, so we don't need to do that one again. That's why it's saying we can get a mixture of compounds. So this could also form a double bond, right? And if that forms a double bond, this is the structure that we're going to get. Bosh, bosh, bosh. Boom, boom, CH2. And the rest remains the same. Sorted. That's it. That is the answer. For 1 mark. But that 1 mark, we had to work for that 1 mark. It wasn't given to us for free. Okay? How are we feeling about that? Sweet. Okay, we've got a bit of a rest coming up in a way, apart from question 10's a bit nasty, actually. All right, I'm going to drink my cold coffee and have a bit of a snacker jack. All right. Apologies. Okay. So, what inspired you to do chem with us for 5 hours? Not that bad, is it? Nah. What? I'm getting paid to what? 7:30. Why have I decided to go to 9 then? Behave. All right, I'll stop at 7:30 then if it's pure that. Okay. Question 9. I'll see how it goes, Pura Shotman. I'll see how it goes. But 12 a.m. people are just gonna fall off. You're not going to cry. Come on. Right. Question 9. Fire away. 1 mark. Come on, let's go. It's not scary. If you go in there scared, you might as well not turn up. You've got to go in there confident. You've got to. Okay? I really mean that. It's not cesium fluoride. Okay. I'll just have an existential crisis trying to figure out where I went wrong in life picking chemistry. Oh my gosh. Everyone's hating on this. This subject is the best. It's D. Why is it D? Let's think about why it's D. Smallest difference in electronegativity. Yeah, I see what you mean. Yeah. Okay. Now, lithium is small. It's a small ion. Oh, I'm not even entertaining for a Shotman, to be fair. So it's a small ion, and it is polarizing. Whereas the iodide ion is fat and floppy. And the fact that it's flat and floppy can mean what? Is exactly, I'm going to go with Habs's reason. The largest difference in size. I'll explain why it is an A in just a sec. But look, if that's fat and floppy, what's going to happen to this electron density with that small charged ion, which is highly polarizing? The electron density in that cloud is going to do what? It's going to be pulled towards the... It's going to be pulled towards the lithium. So if it gets pulled towards the lithium, look, it's a bit like having some Play-Doh. If I pull that Play-Doh, those charges, that electron density isn't localized on those ions anymore. It starts looking more and more covalent, right? That's why, because that large mismatch in size. We'll take cesium. Cesium's fairly big. You cannot be writing floppy in your exam tomorrow. Don't write floppy. Not so much mass to charge ratios, more sizes, okay? So fluoride is small. Okay, the fact that cesium is large, can it polarize the F- ion much? And that has a deficit of electrons, so that's not going to be pulled towards the, yeah, ionic charge density for sure. It's not all about nuclear charge and shielding. I would say ionic charge density, okay? Ionic charge density. So this is not going to be polarized much. The cesium iodide also isn't going to be polarized much, and plus cesium and iodide are similar, right? So these guys aren't going to be polarized much. Now, why doesn't the lithium polarize the fluoride? Well, the fluoride is of a similar size. So what we're really looking for here is a mismatch in size between the positive ion and the negative ion. Small ion, big anion, lots of covalent character, okay? Yeah? I wouldn't go with that, Robbo, but if it works for you, go for it. In terms of electronegativity, I don't like it, but whatever works. Whatever works. I would go from sizes because the size and the charge determine what happens. Polarizing means it will pull electron density towards it. That's what polarizing means. So polarizing pulls electron density towards it. And polarizable, if something is polarizable, we're normally talking about anions being attracted to the cation. So something is polarizing, we're looking at cation. Something is polarizable, we're looking at the anions and its electron density going towards that small positive charge. Okay? That makes sense? And plus, it hasn't asked us to explain it, so whatever works, really. Yeah? Okay. Let's move on. Aminosite, lovely. All right. I'm just going to tell you this now. This question on mine is different to yours. Can you change your values now, please? So change the molecular weight and the element stuff, please. Do that now. What's the actual score? Just have a quick look at the score. Oh, it's 1-1. 1-1. That's what BBC Sport says, no? Wow. Right. What do we think when we see this question? I mean, I'm not going to... Why did I ask? No, I'm not watching either. Too stressed about Kev. All right. Let's smash this question, okay? You see hate for Kev. It's not bad. It's not bad, right? Before we do any of the mathematical stuff, what are we thinking in terms of tests? So, what are the tests for these ions? As if you're not bunning, Chem. You love it, really. So stop moaning. Right. Yes, Nathan, it's NaOH. Absolutely. So, for NH4+, let's do the test. The test is Can I just do the ionic equation? It says ionic equation, so I'll do the ionic equation. So you add sodium hydroxide and you make NH3 plus H2O. That is the test, okay? Yeah, damp red litmus is going to go blue. Red litmus goes blue. Good. Nice. AL3 is not just a flame test. How do you take a break whenever you need? I do mean that, okay? You can just pause and watch it from the next part, okay? Right, the test for Al3 plus. What is the test for Al3 plus? Well, Al3 plus in solution is going to look like this, isn't it? It's going to be hydrated. It's going to have water ligands around it. So what do? We add 3 hydroxide ions and we're going to get a white precipitate, okay? A, green solution. Aluminium, white precipitate, okay? So we're going to get, it's an acid-base reaction. Solid, and that's a white precipitate. Plus 3H2O. Good. Add it in excess and it will go colorless. No worries. I was just like, what? Okay, add one more equivalent of OH minus and we're going to get, so that white precipitate redissolves in excess OH minus. Yeah, we all good with that? Cool. All right. Finally, what is the test for the sulfate ion? Anytime you see sulfate ion, you should be thinking the test for that is add barium chloride. So barium chloride is soluble. So barium 2 plus SO4 2 minus AQ makes barium sulfate solid white precipitate. Wait, what was that differentiate to? We'll do some of the transition metal stuff later. We'll do some of the transition metal stuff later. But the aluminium one redissolves. The copper one as well, when we do copper. Okay, so those are my tests and those are my ionic equations. All right, cool. I tell you what, Abs, I didn't put any in, but on the next break, shall I tell you what? Shall I put in some chromatography from the Easter revision course? Just so we're like, it's fresh in our minds? And DNA and that stuff? Sweet. That's cool. Okay. You would add barium chloride, not barium, okay? So the test for sulfate is add barium chloride. Remember, you have to have reagents that actually exist. Cool. Lovely. Yep, sweet. Okay. I'm going to rub this stuff out now, if that's okay. Can I rub it out? And then I'm going to go through the empirical formula calc. Speak now, or I'm going to... I've got rates in here as well, and I've got some hard rates questions in here. But as everyone knows, rates is probably the best topic. My favorite topic, probably. Okay. What else is a white precipitate? I'm trying to think. Or come back to me, Mohammed. Right. What? No other white precipitate? Is it because I said rates is my best topic? All right, so let's do an empirical formula of this. Okay. Yeah, rates is the best. Who's going to agree with me? Nancy, Mohammed? Thank you. No, like, Is rates the best topic? Yeah, it's the best one. It's a beautiful topic. Thank you, Mohammed. Thank you. Right. So what we're going to do, we've got the percentage by mass. Just going to say, yeah, it was out of 100. Okay, great. Wow. What's your favorite topic then, people? Okay, so I'm just going to go through the motions. I'm going to divide this by the AR, not the MR. A means left field. Left field. Okay, wasn't expecting that. Not chem. Come on. Transition metals is good. Aluminium is 27. Sulfur is 32. Oxygen is 16. All right. Let's put some numbers in here and process this. Okay. Let me know if these are right and try and do it independently. 6.18. 0.22. Guys are actually making me laugh. I've got a zero orders question if we want to revisit that. Okay. If you get a concentration time graph that looks like this, it's zero order. Okay, so we've got the moles. To work out the ratio, what are we going to do? Divide by the smallest number of moles to get the simplest whole number ratio. That's going to be 0.22. 0.22, 0.22. Cool, so that's going to be 1. That's going to be, what, 28? Blimey. Okay. That is 1, that's 2, and that's 20. Okay, cool. Done. For zero order, when you've got a rate concentration graph, and it's like that, then it's zero order. Concentration time has to be a slope negative gradient. Straight line. Okay, so this is going to be concentration over time should look like that then. 100%. Zero order. No questions about that. Okay. Now, what do we know here? How are we actually going to work out this formula? There's many ways to do this. There are many ways to skin a cat, as we know. So what are we going to do? Any suggestions to what we do next? Hello? Yeah, there's quite a few things that we could do. MR of known, then minus it from that. Absolutely. Okay, cool. So, good. So, what do we think the MR of the known thing is? What do we think the formula is of the compound? Okay, exactly, right? So, we've got 2 sulfurs. So, the fact that we've got 2 sulfurs, how many sulfate ions do you think we must have? We must have 2. Agreed? That's one way that I would look at it. Okay. So that's minus minus 2. So that's minus 4 in total in terms of charges. So now I need 1 NH4 and I need 1 aluminium. Sorted, sorted. Okay. Okay. There's many ways to do this actually, but that's what it is. Okay, so what we could do next is we know the weight of the hydrated one. So the hydrated compound equals 453.2. Okay, so why don't we work out the MR of this? Does that make sense? So let's work out the MR of that. If anyone's done it, put it in the chat because it just saves some time. So 14 plus 4 plus 27. plus 2 plus 32 plus. Do we get 237? Unhydrated has an MR of 237. Nice. Okay, so what's the rest of that mass? The rest of that mass must be, so the difference equals mass of water. Okay, agreed? So let's take the difference. So it's going to be 453.2. Take that away, and I get a difference of 216. Yeah, it's 12. 216 of water. Okay, should be grams per mole actually. Okay, how do we finish it off? So what do we do? So then divide it by 18 to get X. That's how I would do it. So then divide that by 18 to work out the number of moles of water, and that is 12. Sorted. Yeah, that's the whole number ratio. Coming. Yeah, sorry. So find the ratios, work out the difference in NMR, then divide by 18. I can put myself top right, yeah? Hang on, I'll just get out of the way. How's that? Right. All good? That is a smarter way of doing it. Thank you. Sorted. Is cold a good thing? Okay, let me know when you're done. There was another way to do it though, because we went around the houses a bit. Units are unitless because it's a ratio. I did. I'm old. Absolutely, Mohammed. I'm proud of that as well. You're right though. Hang on. Somebody said not yesterday, a couple of days ago. I was talking about work anyway, but they used an acronym, SS. No, Mohammed's right. And straight away, I was thinking spreadsheet, and then they started laughing at me because apparently SS doesn't mean spreadsheet. So what does SS mean? I didn't know that. They found it hilarious. Yeah, I got all right. I know now. Every day's a school day, isn't it? Unbelievable. Unbelievable. Right, what are we doing? By the way, I was going to say there's an easier way to do this. Okay. Once you've figured this out, once you've done this bit, how do we get the rest? You know that 4 hydrogens are. Oh, way more. Wait, anyone over 30 abbreviates spreadsheet to SS. Like, that is a thing. Who abbreviates screenshot to SS? I've never heard of that. Unbelievable. You could have just put a 12 there because 12 times 2 gives you 24 plus a 4 gets you to 28. Sorted. All right, can we move on from this question, please? Okay. Where are we? Right, these are... Yes, I told you I'm not, Mohammed. I'm not making this up. I'm familiar with what a screenshot is. I didn't know the abbreviation. Right, let's have a look at question 11. I don't know what that is. Right, but I do know what enthalpy of lattice dissociation is. So, this is the enthalpy change when 1 mole do I have to get rid of that? I'll remove that. Sorted. Yes, let's lock back in. Right. Enthalpy of lattice dissociation. What was I even talking about? Right, it's the enthalpy change. The enthalpy change when 1 mole of ionic solid dissociates into its gaseous ions. That's it. We could do a little equation. So, for example, NaCl has to be in the solid state, and you're going to generate Na plus gas plus Cl minus gas. Out of curiosity, what would delta H be for this? Is it exo or endothermic? It's positive. You're putting energy in, right, to break that up. So this is I put loads of questions in just so we had more, Aisha. Cool. Yes. Where are we? Draw a labeled cycle to calculate the lattice enthalpy dissociation of ammonium nitrate. Shall I speed up a bit? So NH4NO3. I'm going to redraw this. Goes to NH4 plus NO3 minus. All right. So that's my solid. I'm forming my aqueous ions here. Hey, some people are on it. So we break that up, we go to NH4 plus gas plus NO3 minus gas. Okay, what information do I know? I'm going to annotate that label as at arrows 26 plus. I know the enthalpy of hydration, that's minus 308. I know the enthalpy of hydration there, that's minus 316. So that's my X, okay? So how do we do Hess cycles like this where it looks a bit funky? What do we do? It's my clockwise arrows. So that's a clockwise arrow. That's anti-clockwise. That's anti-clockwise. Can't spell. And that's anti-clockwise. Okay, cool. So what are we going to do? We're just going to say X minus 308 minus 316 is equal to my clockwise arrows, which is plus 26. And this is my anti-clockwise, okay? So then X is simply going to be equal to 26 plus 308 plus 316. And what do you get? 26 plus 308. Do we get 650? Yeah? Good. Got to put the plus. 3 marks. Done. All right. Any questions? I was going to ask another stupid question, but I don't want everyone to go into hysterics. So I'll wait. Okay. Say that again. All right. Just where did this cooked thing come from? Where has that come from? I'm cooked. I mean cooking food. Right. Thank you, Phoebe. I get. I don't know. I just want to know the origin of it. I've never seen Breaking Bad. Never seen it. I see. Okay. Right. Shall we continue or not? No, no, no. I'm not banning it. Or cooking means you're doing great. Okay. Right. No, no, no. I'm not banning it. It's gonna be a long night, isn't it? Okay. We're at question C. Enough. 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 Right. I'm gonna have a bit of coffee. It's cold coffee. Right. Do you want to do this question or not? Have a look at it. Yeah, happy to go to 9. Do you want to do this question for 3 marks or not? One for skip, one for yes. Yeah, it's Q equals MC delta T. Yeah, let's skip it because we've done a few like that. However, all right, we'll skip it, but just as a, what do you reckon then for D? I don't want you to actually do it, but remember, we're measuring the temperature, right? Phoebe, that was an enthalpy change of solution. The top one is the enthalpy change of solution. Okay, it's going to be 0.1 times 2 over delta T. Lovely, good. Can we not skip it? Okay, I'll really quickly do it. I'm not going to talk through it, I'm just going to, so Q equals, so the difference here equals delta T, so that's going to be 20.2 take away 12.2 equals 8. Cool, so it's endothermic. How do I know it's endothermic? The temperature decreased. Okay, cool. So Q equals 25, tells me the density is 1 gram per centimeter cubed, so it's going to be 25 times 4.18 times the temperature change, which is 8 as well. Okay, so Q equals plus 0.836 kilojoules. All of that divided by 1,000. Plus sign because it's endothermic. Okay, finally, delta H. Oh, wait, this is delta H solution as well. So, should be all right, Phoebe. Okay, so I've got my Q. So it's 0.836 over the mass. So the number of moles of that solid dissolving. So that's going to be 4 over the MR of that, which is 80. And that gives me plus 16.7 kilojoules per mole. Right. So what is the uncertainty going to be? Because we're measuring the temperature by difference, it's going to be twice the absolute error. So it's 0.1 times 2 over the actual value, over 8 times 100. So it's going to be 2.5%. Cool. All right, we've seen quite a few of these today. Recommend a change to the student's method that would give you a decrease in the percentage uncertainty. What are we saying then? Because we want a larger delta T, right? If we want a larger delta T, what could we add more of? Yeah, add more mass of solid. Absolutely, done. You could say smaller volume of water because you're adding a solid and water. It will allow that. More sodium nitrate, done. You can't say concentration of sodium nitrate because sodium nitrate is a solid, okay? So, you got to be specific with your language. Language is important. All right, so what I'm going to say is use a larger mass. Shall we just go till we're done? As in, like, done the whole booklet? Larger mass of NH4 NO3. Reason. What's the reason for this? Because it's going to give us a larger delta T. And if it gives us a larger delta T, we're dividing by a bigger number. The percentage uncertainty goes down. I have no idea how long it's going to take. Right. F. Why do you reckon there's some people who've got different results? So some people got 15, plus 15, and the accurate value is plus 26. Because we're dissolving a solution, because we're dissolving a solid, we could say incomplete dissolving. Thank you. Why can't we say heat loss to the surroundings? Why can't we say heat loss to the surroundings? And it's not incomplete combustion because you haven't read the question. It's not a fuel though. Yeah, exactly. It's endothermic. Exactly. Because it's endothermic, you can't say heat loss to the surroundings. I guess what you could say is what? What could you say? Heat gain from the surroundings, I suppose. The opposite, right? That would work. Cool. Not side reactions as well. So just incomplete dissolving. Heat gain from the surroundings, I would suppose. That would work. I'd normally just go incomplete dissolving when you're doing that. Okay. Do we want to do a Gibbs question? And shall I just do it quickly? All right. Okay, so utilize data from the above and .OH value from the equation. See if the enthalpy change of the solvent is 0. Okay. All right. Sweet. So basically we're working out delta G. Okay, cool. Delta G equals delta H minus T delta S of the system. All right, on this question, think of your units. Those are in kilojoules, those are in joules. So delta H is 26, so let's convert that. Let's convert the system into, let's convert the system into kilojoules. So delta H, because delta G is in kilojoules. All right, so we're going to leave that as 26 minus, going to put brackets here. So it's 298 times, okay, do I have to work out delta S of the system as well? Long. Okay, cool. No worries. Delta S of the system is going to be the sum of the entropy of the products take away entropy of the reactants. Sweet. So entropy of the products is going to be what? These two added together? It's going to be 113 plus 146. Take away the reactants, which is 151. So I get plus 108. Plus 108. Have definitely next break, I'll put some in, okay? Do you guys still have access to the Easter revision course out of curiosity? Times 108 over 1,000 because I want to go from joules to kilojoules. Okay, so what does that give me? So 26, take away that answer. I get minus 6.18 Sweet, sorted. Done. What does that tell me? It's feasible. Because delta G, if delta G is negative, then feasible. All right, cool. No, till a few weeks ago. All right, cool. No worries. It's 7:15. What are you saying? That's a 2 marker. Okay, I'm just gonna go through how to do this one, and I'll move on to the next bit. Okay. I reckon we can get a fair bit done in the next 15 minutes if we just grit our teeth and get through it. So what we're gonna do here is set delta G equal to 0. So that becomes T delta S equals delta H. Rearrange exactly, so that's going to be delta H over delta S. So that's going to be 123 times 1,000. And the entropy change is 144, so that equals 854 Kelvin. So that's your 2 marks, okay? Cool. All right, we've got a fair few... Okay, cool. All right, 12 is ozone absorbs UV radiation. Done. Okay, EMF cells question. Okay. So the way that we read this is that species is oxidized, that species is reduced from left to right, okay? That's the convention that we use. Now my lot should be like bang on this. Yeah, it's A. Yeah, that's your sort bridge, the 2 lines. This one is A, absolutely. Because what's happening is if that species is being oxidized, we're flipping that. This is the anti-clockwise rule. So that's being oxidized, this is being reduced. So remember E cell. Nathan, the ozone one was D. So the way I do E cell is E ox plus E red. So this is the reduction potential. So the oxidation potential is going to be that number, but flipped. So that's going to be plus 0.45 plus 0.33, which gives me 0.78 volts. Okay. There's another way to do this, that E cell is equal to E right-hand side, take away E left-hand side. If you like that, go with it. I don't like it, but it gives you the same answer, okay? It's the same sort of way of doing it, but it's A. Okay. Big rates question. Yeah, there are ways to teach, but that doesn't show... I mean, yeah, that gets you the right answer. That gets you the right answer. More positive takeaway, more negative. No, there's no one correct way. There's no one correct way. The more positive one is that one because it's being reduced. Take that away from the negative one is fine, but it's actually EOX plus E red. That's really what's happening. But E cell has to be positive for it to be feasible. Okay. This is a big rates question. Do you want to take 5 or not? I mean, I'm happy just going on. Okay. Cool. Take... Nancy's like, nah. I think this is quite a chunky question. I think if you don't want to break, just take some time reading it and annotating it, thinking about how you would answer it. If you do want to break, take 5. Cool. We'll take 5. I'm just going to grab... I've got some Snacker Jacks. They're pretty disappointing, though. Cool. All right. Catch you in a sec. Hello. Hey everyone. Okay. This is a tough question. I'm not gonna lie to you. If you get something like, I'm not saying it's undoable though. We've got to know the logic behind clock reactions, okay? I taught my class. Nancy, you can say yes. Mohammed, you can say yes. Efez, you're not here, but you can say yes. Fawaz, you can say yes. And we went through it in detail as well. 10 p.m. Can you imagine? Let's do this. If you're in my class, if you're in my class, did we go through chromatography and GC? My cat's here. Umo, thank you. Right, we did it properly. So, you know, you've always got that. Oh, really? Okay. The more detail you know, the more prepared you are for the exam. Cool. Go on then. Let's do it. What if that doesn't want to go until 10? All right, let's do this. Yeah, I think that's a good point. I think Robbo's point is important. If it goes off task, keep it private. Did it happen in bio? Now let's keep it like this then, because we got to stay locked. We got to stay focused. No, let's keep it like this then. Sweet. Bio was so weird. Yeah, allow that then. Okay, we're just gonna go on. We'll keep it us. Cool. Right. Right. Rates. Clock reactions. Okay. What's going on? Describe by having a large surplus of the peroxide. Okay. First thing we need to know is in a clock reaction, you've got two successive reactions, okay? You've got two successive reactions going on. So as soon as one reaction, the next reaction kicks in, okay? Don't tear up because of chemistry. Don't let it do that to you. If you need a break, have a break, okay? So let's have a look at what's going on. So describe why having a large surplus of the peroxide and the iodide ensures that the reaction rate at a constant temperature is solely influenced by the concentration of H+. Okay, I'll draw this out. I'll try to draw this out, okay? So this is H2O2 in that light blue color, okay? This is I- in red. Can't say limiting reactant, doesn't get you the mark. Doesn't actually get you the mark, okay? So this green is the H plus. Now, let's say let's say let's say this much H2O2 reacts, so I minus reacts, and that much H2O2 reacts, okay? Now, the fact that the H2O2 and the I minus are in such a large concentration, so the H2O2 and the I minus are in such a large concentration that even when that much react, is their concentration going to go down significantly or not? What are we saying? Exactly, because they're in such a large excess, okay? So even though they react, and they do react, there's such a large surplus of them, it makes absolutely no difference, okay? So it's a bit like me weighing 150 kilos. I mean, I don't, but if I lost 1 kilo, is that going to make a difference? No, it's still roughly 150 kilos, okay? That's the point. You're in such a large amount of it, it's not going to change the concentration significantly. So if it doesn't change its concentration significantly, is it going to affect the rate? The concentration's not changing, is it going to affect the rate? No, it has no effect on the rate. So that the concentration change is, hang on, let me think of a best way to word this. No, that was rubbish. So that their concentration doesn't change, so they have no effect on the rate. That's what I would say. So no effect on the rate. So their concentration is effectively constant. Yeah, what Venki said. Cool. Right. Another nice question. Okay, think about this one. So you've got portions of the reaction mixture taken at specific intervals, titrated with a base to ascertain the concentration of H+. Sweet. Indicate and justify the procedure that must be followed for each sample prior to titration with the base. Okay, what do we have to do? So we're trying to work out the concentration of the H+ at a specific time. Yeah, good. Dylan, nice. So we can quench it. Quenching means to stop the reaction. Okay? Because we want to find out the H+ concentration at that specific time. So what do? We quench it. So first mark for saying quench. Quench is just another way of saying stop the reaction. Second mark is for how we stop the reaction. How do we stop it? There's many things we can do. The cooling is the best way. Done. 2 marks. Sorted. Yeah, or dissolve in a large amount of water. Why do you not neutralize it, Els Bells? In fact, you would lose a mark if you said neutralize it. You're trying to work out the H+ concentration. If you add shed loads of alkali at this point and then try to do a titration, there's not going to be any H+ left. So you can't do a neutralization at this point because you're trying to use a neutralization to work out the H+. Yeah, stop the reaction is fine. You can't, denature would be for biology and protein, so you can't do that. So you literally, how would you quench it? By cooling it, by surrounding it by an ice bath. So there's a reaction going on in here, there's a reaction going on in here, and what we do is we literally put it in an ice bath. And that stops it. You dash it in ice, bruv, exactly. So what it's saying is, what do you do before the titration with a base? So the thing you do before the titration with a base is you quench it and you cool it. And the reason for that is that makes sure that the H plus concentration doesn't change anymore, because you want to know the H plus concentration at that specific time. Why cool? Because that slows the reaction down. Heating something up increases the rate of reaction. Cooling something slows the rate of reaction. It's like when you've got your spinach, you're cooking your saag or whatever. If you're cooking spinach and you just want to blanch it, you cook it in boiling water first, and then you put it into ice water, and that stops the cooking process, right? Same thing. Yeah, it slows to a standstill, that's it. Okay. It's good enough. It stops it enough. Right. How does the graph demonstrate that I could handle some proper saag? That would be nice. How does the... If you don't know what saag is actually a curry made from mustard leaves. Not spinach, mustard leaves. Proper saag, anyway. Anyway, why are we talking about cooking? How does the graph demonstrate that the reaction order with respect to H plus is 0? Yeah, exactly. The rate stays constant. I know I am. It's my own fault. Apologies. The rate stays constant, and the rate is the gradient, correct? The rate stays constant. Okay, so first mark is the rate stays constant, even though what is changing? Even though the H plus concentration is decreasing. So this does not affect the rate. Good. And actually here, the rate is equal to the gradient. So the rate is a constant. Okay? Because is everyone happy with that? So that's where the 2 marks are coming from. Cool. Did this question come up in paper 2 or a variation of it? Aha. Okay. Okay, draw the graph. Okay, cool. Righty-ho, 3 marks. 3 marks for this. Use the graph from the previous question and calculate the value of K1. All right, cool. Go on then. Can you calculate the value of K1? That's pretty straightforward. Okay, so yours probably is easier to do. So let's go to, I don't know, what we go into. It's going to be hard to see on here because the intervals aren't enough. But remember that the rate is the change in the concentration over the change in time. And the change in concentration with time is a constant, so rate is a constant. So let's do this. That's dy by dx. So that's going to be y2 take away y1 over x2 take away x1. Okay. So yeah, we're just working out the gradient. So y2 it's going to be negative, but let's just pick these 2 points. Is that change in the y-axis? Is that 0.2? Is that 0.2? So if that's 0.2, what is the change in the x-axis from there to there? About 160, 165? Let's go 165. Okay, roughly. About K1 is just the rate constant for that. We said that's K1. Okay. Right. Hang on. Just give me 1 sec. Give me 1 sec. K1 is just the rate constant for that. Give me 2 seconds. Just gotta close the door because there is crying, but that's okay. Okay, so 1.2. So K equals 1.2 times 10 to the minus 3. Yeah? And the units are going to be moles. Dylan, it's quite hard for me to do. Actually, do you know what? Yeah, you're fine. All right, fine. No, I didn't see those. I didn't see those. Why wouldn't you use a paper instead of doing your own small lines? Oh, we have to use, we have to modify the questions. So we have to redo them, which is quite a lot of work. No, you're right. You could do it this way. I didn't see that. So that's going to be, so dy is equal to what? 0.1, 0.3. And that is 250 dx. You should get the same answer, really. So 0.3 over 250. Yeah, 1.2. Good. I mean, it should give you the same thing, right? And it does give you the same thing because the rate is constant. So there you go. And the units are moles per decimeter cubed per second. We happy with that? That's what it's asking. Thank you. Cool. What do you mean, why is it that? However, here rate equals K. The rate is the constant here, right? Because the rate isn't dependent on the concentration. So the rate is simply K here in this case. Yeah? So when it's zero order, the rate equals K because this is a constant. So if you want me to do it like properly, so we're saying rate is equal to dc. Can I just do it? Yeah, you're happy. You're all mathematicians, aren't you? dc by dt, which is equal to k h plus, right? Cool. You don't do that. Okay, fine. Well, look. This is zero order. If that is zero order, that becomes 1. So this is going to be simply, the gradient is actually just equal to k. Do you see how that works? Yes, negative value as well, I should have put. But I don't think it care about the negative value here. Just the value and the units. But it is a negative slope, so put the negative sign. Exactly. Nathan, was the question about the Arrhenius plot? If you get given K1 and K2 with 2 different temperatures, okay, I know what you're talking about. So yes, you have to use that and take the difference. You're basically doing 2 unknowns, right? Kind of. Yeah, because you're doing it at 2 different temperatures. You're doing it I know which one you're talking about. I'll think of an example of where that's come up. I know what you're talking about, though. Yeah, I haven't got that here, but I'll try and find something on that, okay? Right. We've done this. Okay, so the next question for 1 mark is 2 marks. Plot a graph. Okay, Nathan, tell me the paper and I'll try and find it. So, okay, so let's have a look at this. So we're getting 2 marks just for plotting a graph, okay? So, that's 0. Yeah, we can skip this. Is that okay? I mean, we missed this mark as well, but we're just drawing a tangent. So I'll show you how to do that, okay? So what you're going to do is you're going to get a graph which looks like this. I won't do it. You're going to get a graph which looks like this or whatever it looks like. If it's a curve, do it as a curve. So if it wants to know the reaction rate at 0.35, It's going to be somewhere like here. There's your point. You draw a tangent to the curve. Don't do that. Doesn't cut through the curve. Just touches. Like that. Show on the graph that you can actually do this. So that's your change in y. That's your change in x. So dy by dx equals the gradient, which is equal to the rate at that point in time. Yeah, time is going to be on the x-axis. Remember, rate is defined as the change in concentration per time. So it tells you which axes they are. So concentration on y, time on x. Cool. Right. Yeah, if it gets completely used up, it would touch 0, right? If it's a reactant, sure. Unless it's in excess, and then it wouldn't. Okay. 6 marks. Have a read of this question. Just take 2 secs to read it. I'm coming back. It's 6 marks. It's not just going to be as simple as that. This is a nasty, nasty question. I'm not going to lie. But what do we think about this? Can we put some thoughts in here? Right. Right, let's actually be collaborative on this question. Let's see what we're saying. Disappearing cross, stop reaction at regular intervals and quench and plot a pH curve. Okay, good ideas. Anyone else? It's 6 marks, remember. So they're not giving this one away, you know. You got to work for this one. All right. Should we go through it? It's a variation of a clock. Yeah, absolutely. It's a variation of a clock. Correct. So you could find E-conc using calorimetry. Yes, you could. Nice. Very good. Could definitely go on the calorimetry route, okay? Could definitely go on the calorimetry route. I'd do it slightly differently, but calorimetry would work if you know how you're going to write it up, okay? So this is how I would do the question, because I'm just going to... If you go calorimetry, you're going to have to use logs and stuff. So if you're not a mathematician, it could get hard. So what is the first thing that we're going to measure out? So we got all these guys, A, B, C, and they're going into D and E. Now, when E is made, what is the E going to react with? The E is going to react with X. So who cares, right? Forget about RDS for just a sec. Forget about RDS for just a sec. So the E reacts with X and it gets used up. So what's going to happen when the X runs out? So we're adding a small amount of the X. No, you don't need to know the equations off by heart, but you need to understand the logic behind them, okay? And this is the logic behind an iodine clock, say. So let's say the X runs out because we're adding a small amount of X. So if we're adding a small amount of X, what color change are we going to see as soon as the X runs out? It's not an equilibrium reaction though, Mohammed. So it's a rates question here. So the E is reacting with X to make whatever. So exactly, Abs. Nice. So as soon as the X is consumed, yeah, we have got more practical questions. These are all paper 3 questions. It's going to go from colorless to blue-black because the E is black in color. Yeah? Does that logic make sense? So there's successive reactions. So as long as we've got X, when X is present, it's colorless. However, as soon as the X, a small amount of X gets used up, bang, blue, black, just like that, okay? Instantly. And it is lovely, this reaction, when you see it. It goes bang, just like that. Okay, does that logic make sense so far? Are we happy with kind of how clock reactions work? Okay. All right. Yeah, okay. You need starch as an indicator as well. Yeah. I mean, you don't need it for this because we're not looking at the iodine clock. Yeah, but in the iodine clock, you'd have starch there as well to make sure we see that blue-black color. Yeah? Is X, A, B, or C a separate reactant? Well, I guess that's my question to you. How are we going to add all of these reactants? Because we need them in one pot, right? So the order matters. The order does matter. So we put them all into one jar, but the way that we put them into the beaker or whatever matters. So the first thing that we need to do is to take known volumes, and this is my answer, known volumes of A, B, yeah, exactly. This is a clock reaction. It's an iodine clock in a different context, correct? So we're just applying the same logic to something we might not have seen before, but the logic remains the same. Yeah, X is a different reactant. So if this is a reactant, this is a reactant, this is a reactant, and X is a reactant as well. But it's separate to A, B, and C. Hence it's X. So we take known volumes of A, B, C, and X. So in one beaker, we can take A. The dark blue color only shows up when all of X is used up, correct? Okay. So we add A, we add B, and X in one container. Why don't I just add all of them in one hit into one container? Because if I add all of them in one, the reaction will start. Fatima, correct. So you take A, B, and exactly, they just react. Excellent. Really, really good, guys. Els and Jazz and Fatima, excellent. Yeah, and because the reaction would have started, correct. So let's just draw this out. So for point number 2, so I've got A, I've got B, I've got X. Are they going to react? No, because I haven't added C. Okay, good. So what's my step C going to be? We're going to add C and set A. Remember, it's a rates question, so we need to measure what quantity. We're going to start a timer, right? Absolutely. Good. I'm really impressed. It's 5 to 8 and we're still going. We don't assume that, Robert. We know they don't. Look. A and B only react with each other when you got C in there as well. Oh, yeah. Yeah. And the thing is, X is only going to react with E because it tells us that. What is A? Who cares? Yeah. So it didn't even matter that I'd used A and B first. I could have chosen B and C and then add A. Like, the order doesn't matter, but the thing is, you can't add all of them in one hit. That's the point. Are we happy so far? Yeah. All right. So then we add C and set a timer. So we hit go. Okay, tell me what to draw in here now. What am I making in this? Yeah, assume they don't react because it tells you they don't react, that the E is the only thing that is made in reaction 1 that then reacts with X. Okay, so we've got we don't have A, B, and C because they are making E. Yeah? So we're making D and E. However, as soon as E is produced, what happens? Because we've got X in here as well. These guys react to make something else. Agreed? But there is a small amount of X. So as soon as X is used up, what happens? We've got E, which is left over. And what color are we going to see? Bang. Turns blue. Stop timer. Yeah. Do we see how this works? Exactly. E and X react to make a... No. No, E and X don't react to make the black precipitate. E is the precipitate because E is dark blue. Okay? However, think about it this way. So E is made in reaction 1, but as soon as E is made, it doesn't have time to go black because as soon as it's made, X reacts with it to make whatever. Yeah? Fatima, you don't have to give details of the actual volumes, just known volumes. But when X gets used up because there's only a small amount of it, the leftover E gives us that blue-black color, okay? Do we see the logic here? So yeah, so you could say that the cross is disappearing if you're doing it across, but you could just do it at timer as well. You don't need to say anything about the concentrations of the reagents until one bit now. Okay, so I'll talk about that bit in just a sec. Yeah, so first reaction, second reaction, okay? So these guys react, make E, E reacts with X. So after X is used up, we see E is the blue-black color, cramming, correct. Bingo. So record the time taken for the dark blue to appear. Okay. Now, what are we going to vary? Because we are going to change something, right? What are we trying to see? We're trying to determine the order with respect to A. So whose concentration are we going to change? Lovely. We change the concentration of A. Beautiful. Change concentration of A. Whose concentrations do we keep the same? Use same concentrations of B and C. Yeah. Okay. Exactly. Good. So then what are we going to do? Then what? True, you are right, Mohammed, but how are we going to do that? We're going to plot the rate. Yeah, same amount of X as well. Same number of moles of X. So then we're going to plot a graph, aren't we? We're going to plot a graph of the rate. Now, yes, Fatima, exactly. Now, we don't know the rate directly, but it's an initial rates method, right? So we don't know the rate directly, but the initial rate is proportional to 1 over t. So we can assume that the initial rate is 1 over t. Does that make sense? So we're going to plot the rate, i.e. 1 over t, versus what? The change in concentration of what species? Of A. Exactly. Good. Don't worry too much about this, but think about this. Let's try it this way. Rate is proportional to 1 over T. And what I mean by that is if T is large, the rate is what? If T is small, the rate is high. Yeah, exactly. That's it. Tables that they give us in rate calculations. You'd have to do a graph. No way of not doing a graph for this one. Unless you do something continuous like absorbance. Yeah, it's slightly different to one of those initial rates where you've got the... Yeah, if you get a question like this, then you should be sorted. Okay, so what I'm saying is, so we're going to get a graph which looks like this. Okay. Let's say we get a graph which looks like this then. So we've got a rate concentration graph. What does that tell you about A and the rate? What order can we infer from this? L's bells. No, because we're only trying to find the order with respect to A. If we wanted to find the order with respect to B and C, we would do it that way as well. Okay. So this would be 0. What would this be if we get that? And that would be second. Okay. So just be really mindful. Take your time when you're reading this stuff. And just take your time. So think about what to plot where. Okay, and just when you're I've rushed the last bit, but just annotate this. Show the examiner what you're doing and what the inference is here as well, okay? So determine the order from the 1 over time concentration graph or whatever, okay? That's a hefty 6 marker, but did we kind of understand the logic of iodine clocks and stuff now? Because once you get it, it's not that bad. And I think people think they are bad, so they might come up. You guys are doing well. Okay. Can we have a break? I mean, of course you can have a break. Is this iodine clock? It's a variation of the iodine clock. I say we carry on. 10 minutes. I say we carry on. I can drink cold coffee, but I can't drink cold tea. Oh, God. How long do you want? Cool, blimey. You sure? I'm giving you the choice here. Robbo, you sure it's your last chance? Thank you, that's not true. You can go whenever you want. Anthony, how on earth do you think I know how to do a vote on this thing? I've got no idea. Anyway, so we sure? Tell me if you want a break. Tell me now. All right, cool. All right, question 15 then. All right, 15. Come on, let's go. Write the answer in the chat. Uh, I haven't gone over continuous rates methods today because we are time limited. You're welcome, Robbo. It's D, isn't it? It's raise the partial pressure of nitrogen. All right, cool. Okay, aspartic acid, fine. We're looking at aspartic acid in high pH. All right, so A gives us what aspartic acid looks like normally at pH neutral. So at high pH, if you raise the pressure... Okay, cool. So look at the pressure here. So we've got 4 gas molecules to 2 gas molecules. Raising the pressure of one of these species, like raising the concentration of one of them, so it's going to move to the side to alleviate or undo that pressure. So it goes over to the right-hand side. K, be it Kc, Kp, Ka, is only affected by what? By temp. Nope. Yeah. It says without altering the equilibrium constant. So Charles, you're right. So raising the partial pressure would change the yield, but it's not going to change K. The only variable that changes K of any variety is temp. Raising partial pressure won't affect Kp, just like raising concentration in Kc doesn't affect Kc. Yeah? Okay, so let's have a look at A. That will help us. So we got OH minus. That's going to deprotonate here. We got, because it's OH minus, because at pH 14 we're going to have shed loads of catalyst effect, no effect on K. No effect on yield, just affects the rate of the forward and reverse reaction simultaneously. Okay, so that OH minus is also going to deprotonate here, so it's going to be D. Good stuff. Nice. Right. I'm not going to lie to you. For 1 mark, this is a horrible question. But it's really, really good. It's a good question because it makes you think. Shall we do it? If it was acidic, the NH2 would be protonated. Okay. Right, let's do this. Okay. So this is mean on them for sure. It is really mean. I'm not going to draw it out. So this is a contact process, by the way, where you got a V2O5 cat for the manufacture of SO3. You need to know about the contact process, by the way. So let's do an ice table because we're not going to panic. They're trying to catch us out. Let's see if we can catch them out by getting the right answer. I've got it on the front, Nancy. I can't remember. So we've got 2.5, 2.5. We've got none of that at the beginning, okay? So minus 2x minus x plus 2x. Is everybody happy with that? Yeah, I think it's 30. So at equilibrium, we are going to have 2.5 minus 2x, 2.5 minus x, and that's going to be 2x. Is everybody happy with what I've done in terms of the ice table? Yay or nay? Okay, now. Now add them, yeah? All right, so N total, because we're trying to work out the mole fraction, is equal to the number of moles of SO2 plus the number of moles of O2 plus the number of moles of SO3. Okay, to work out the mole fraction, not divide by the MR first, and it's not got to be equal to 4. Okay, so what we need to do is, we're trying to work out the mole fraction of sulfur trioxide. To work out the mole fraction of sulfur trioxide, I need to know what that is, what the NSO3 is, okay? So what I'm going to do, I'm going to say that N total, take away NSO2, take away NO2 is equal to the number of moles of SO3. Does everyone see that? Yeah? Okay. Do we know what the total number of moles is at equilibrium? Because I think it tells us in the question. So N total is 4. Nancy, I think you got it, you know. So 4 minus, this is NSO2, which is 2.5 minus 2x. Agreed? Yeah? Minus NO2, which is 2.5 minus x. And that equals the number of moles of sulfur trioxide. Is everyone happy with that? So this is going to be 4 minus 2.5 plus 2x minus 2.5 plus x equals the number of moles of SO3. Yeah? Everyone with me so far? Have you seen what I've done or not? Yes, so where did the 2.5 plus x come from? From here. Yeah, I'll put 2x in here, fine. No, you're right, it is 2x. So, minus 2.5 minus 2x gives me plus 2x. Minus 2.5 times minus x gives me plus x. Do you see how I've done that, Twonga? Cool. I can't remember where we are. So we're at minus 1. So 4, take away minus 2.5, minus 2.5. That gets me to minus 1. Is that agreed? So 2x plus 3x. Sorry, it's 2x plus 1x equals... Yeah? Therefore... So x equals 1. Does everyone see that? So therefore... And let's use this now. It's a half because 2 times 1, so I know what x is, so that's 2 times 1. The total number of moles is 4. 2 times 1 over 4 is equal to 1/2, which is equal to 0.5, so it's C. It's a 5 marker. Yeah, it's C. Be honest, do I have to tell Neil about the negatives getting people? Like you said, yeah, true. Be honest, did this negative stuff get people in the question? Fair, so I'll tell you. Okay. Well done. Good stuff, people. Right. Remember though, like I think people are saying some good stuff. That took a while. It's 1 mark. That's not going to be the deal breaker. So just move on. And partly what Nancy says, like AQA they're sneaky, in my opinion. You gotta be when you go in there, you gotta be fighting for it. You gotta know where they can try and trip you up. Know those little traps, okay? And be ready for them. Prepare. That's why we're here. We're preparing for it. Should we aim to do one multiple choice? Yeah, exactly. Do you know what I would do, Robert? Like I said, I would look at the paper, tick off the ones kind of that you can do sort of straight away, like on autopilot, that you don't need to think too much about, and then go back to the multiple choice where you might need a bit more time, okay? Yeah, it's meant to be a mark a minute, but you know it doesn't play out like that, right? So you just got to play it by ear. That's what exam technique is. Oh, right, so bung. I don't think we're this is autopilot, bung pressurized. Also, yeah, but don't rush it. Take your time reading about it, reading the questions as well. Ah, okay, yeah. Water is the wrong way around, but that isn't unsafe. That's not unsafe. What's an unsafe thing? They've clamped it here. I mean, why have they got a thermometer in there in the first place? Who knows? They shouldn't have a thermometer or a bung in there. Yet the flask isn't clamped. Look, it's not even got a ket clip on there. So it hasn't got a ket clip on there. They only clamped the condenser. So actually, that might just fall out. So this isn't clamped. They've used glass beads to act as the anti-bumping granule, so that's no big deal, and that's not unsafe, really. I mean, you can get by. Yeah, they've got those small glass beads. Those are going to act as anti-bumping granules. Okay, what other reagent do we need to oxidize propanoic acid? Sulfuric acid. Yeah, it's dilute sulfuric acid, but I don't think they care about dilute or concentrate at this point. They just want to know it's acid. Highlight 2 more errors in the setup. Okay, we've said what those errors are. So one is the water. Water wrong way around. And somebody mentioned it. Thermometer. There's no reason you don't need a thermometer in there. Okay, what is a function of the small glass beads? They're acting as anti-bumping granules. Right. Ooh, E. I'm not going to do another percentage yield one because we've done so many of them. After addressing the, but I mean, the point is you're going to get a percentage yield question tomorrow. How can we separate the propanoic acid from the reaction mixture? Okay, because if they're close in boiling temperature, which they are, you can't just use simple distillation. You're going to have to use fractional distillation. You can't, because assume that they're the same phase. Fractional distillation, good stuff. Okay, we're getting there. Specify a simple chemical test to differentiate. You can do simpler than that, though, Dylan, I would argue. Let's say you've got two test tubes. That's propanoic acid, that's the alcohol. Let's say you add Na2CO3 to both. Not 2,4-DMP, because 2,4-DMP is a test for carbonyls, and carboxylic acids are not carbonyls. There's a simpler test, guys. If you add sodium carbonate to the propanoic acid, what are you going to see in the propanoic acid? You're going to see bubbles. No bubbles. So add propanoic acid, bubbles. No visible change. A carbonyl group is an aldehyde or a ketone. So this is a carbonyl group. Yeah, bubbles. Ah, or that. These are carbonyls. Carboxylic acid is not. It's its own family. Okay. Question 19. What substance can be purified by dissolving in hot water and then recrystallizing as it cools? That is benzoic acid. 2,4-DNP is mostly for Edexcel and OCR. It's a test for carbonyls. We just did it because benzoic acid is what do we call it? It's insoluble or low solubility in cold water. Ah, okay, I understand. Yeah, so you need to know. You can say effervescence. Bubbles is just easier, right? That's non-polar, so that ain't gonna work in ethanoic acid is a solution anyway. Phenylamine, and that can be a solid, right? That is a solid. So this is a liquid, liquid, liquid as well. So that's why it's not the others. So at room temperature and pressure, the only solid there is benzoic acid. So it's got to be benzoic acid. Like, no two ways about it. Right. Okay. Now, I did 20 questions initially. I had no idea how much we'd get through, but this is how much we've got through. For the remainder, what do you actually want me to go through? So did we say chromatography for sure? Yeah? And anything else? Is there something that I haven't gone through? Okay. Arrhenius buffer calcs. As much practical stuff as possible, biochem. DNA, just want to know how to do the nucleotide. Okay, cool. I'm just going to quickly go through. We're not going to do 20. Yeah, I'll do the nucleotide stuff for sure. Okay. Hang on, there's a train going past. All right, I've got like another 35 mins. I've got some NMR questions. Have a look at this question. Tell me if you want me to do it or not. What do we think of this? How do we feel about this one? No? All right, fine. Yes, please. Okay. I'm not gonna. NMR could. Okay. I'm not going to go through the actual answer. I'm going to write it down neatly or as neat as I can given the circumstances. But what I will do is go through it and annotate it, okay? NMR could come up. Who knows? Okay, so we've got LNM and the iron salts. The red-brown has to be Fe3+. Think of iron oxide rust. And that one has to be Fe2+. Okay. Now, when you add ammonia solution to this, the precipitate that you're getting is Fe OH3, and that's a solid. Why? Because we're starting with the hexa-aqua ion, and we're adding 3 equivalents of the base. So this is an acid-base reaction. So we get 3 deprotonations to make this. plus 3 lots of NH4 plus. Does that make sense? Also, what's happening here is another acid-base reaction, but this time we're getting this precipitate, which is green and insoluble. Yeah, these acid-base reactions, sure. It's not substitution, it's acid-base, and I'll show you why. Because here are my 6 water ligands. I'm not going to draw all of them out like that. So the ammonia comes along. It's a weak base. It takes that proton off. Habs, I'm going to do that here as well. So these combine. That is my base. This is my acid. And that's how we get the NH4 plus. But look what we're left with. And if we do that 3 times, we're left with what? We're left with FeOH3, no charge. And 3 more water ligands on there as well. Yeah, do you see how that works? Yeah, I'll try. I'll try my best. We are running out of time, but I will definitely try, okay? Is everyone happy with this first bit? Now, Habs had a question, add the sodium carbonate solution. So this is a weak base. Okay, so for the green precipitate, we get a ligand substitution. We get a ligand substitution, so we just get FeCO3 and we kick out those 6 water molecules like this, okay? And that's a solid. Now, for here, if this is Fe3 plus and we've got a dative bond, what's going to happen? Well, look. In fact, what did we say? We've looked at this effect earlier. If that's small and highly charged, what's going to happen to that electron density? Is it going to be pulled towards it? Yes or no? Yes. It's going to be pulled towards it. If that electron density is pulled towards it, those electrons in those bonds, that OH bond is going to be pulled towards it. Yeah, it's a bit like the negative inductive, right? Good. So what does that mean? Is this a big delta plus or a small delta plus? Is it more polar or less polar as a result? Look, those electrons are way over there. Big. Good. Good stuff. If that's a big delta plus, is it going to be easier to dissociate or harder to dissociate? There you go. So that's why it's a stronger acid. Done. Like, we talked about this concept in a different way, but this concept comes up again in transition metals. So it does seem abstract at first, chemistry, but once it links and clicks, it really can click. Okay? And it is clicking. You guys are coming up with the answers. So go into that exam with bags of confidence. Right. Dilute nitric acid. Dilute nitric acid is a test for what? Oh, wait. Dilute nitric acid is a test for the carbonate ion. So it's not, we don't have any carbonate ions, okay? Because you don't get a positive test. Okay. Barium chloride is a test for sulfate. Okay. No reaction there, but we get a white precipitate here. So this must be, this is a required practical, by the way. What is a positive result for the nitric acid test? Yeah, I'll do that in just a sec. So we get a white precipitate of barium sulfate. So that just means that this M must be FeSO4. Okay, cool. So H plus plus CO3 2 minus. This is from the nitric acid. I'm just going to do the ionic equation. So we're forming CO2 plus H2O. So a positive test for the nitric acid would be bubbles of CO2. Or bubbles, I guess. Can't tell it's CO2 unless you bubble it through lime water. Yeah. Okay. Silver nitrate is a test for halides, as Nancy says, it's a test for the halide ion. The fact that we get a white precipitate means that this happens. So it's white. Yeah, it's chloride ion. White is that, and we don't have a chloride ion here, so L must be. So now we worked out what the cation and the anion is. But they're iron salts, so that's Fe3 plus. So it's going to be FeCl3. Yeah, that's kind of the answer, basically. Hello? Okay, how are we doing? Are we still awake? Or have we had enough? Okay. Okay, I'm flagging a bit as well, but we can continue. Shall we continue? Okay, I didn't put the chromatography question in. Okay, I'm just going to show you a few more questions, okay? Autocatalysis? Take 5, yeah, seriously, like, this is it's been a long sesh. Let me know if you want to do autocatalysis. You had this on paper 1, so shall we move on? I'm happy to move on. Okay, cool. Just have a look. So it's an autocatalysis of the ethylene dioate and the manganate. All right, cool. I'm going to move on then. How about standard electrode potential here? Yeah, I got electrochemistry here, and I got electrochemistry. All right, let's do this one first, and then we'll move on to another electrochem. How's that? It's a really good question. Why am I getting excited for electrochem? Okay. Can I ask you guys to let me know how you are feeling about this one? So I'm just going to do a bit of teaching around this. So look, you got two negative ions coming together. Shouldn't have asked. So you got two negative ions coming together. I mean, are they going to come together? No. It's going to be high repulsion. The fact that there's high repulsion, the activation barrier is going to be high, right? So look, high activation energy. So we've got to overcome that activation energy. An autocatalyst, yeah, I can give you a quick def. An autocatalyst is when the product of a reaction catalyzes the forward reaction. So the product catalyzes the reaction. That's it. Okay, so how does this catalyze the reaction? Right. Okay, so what's happening? So we've got a cobalt 2 plus ion. So the fact that we've got a cobalt 2 plus ion, in the catalysis bit, the cobalt 2 plus must be oxidized to what? Cobalt 3 plus. Do we agree? And do we have a strong enough oxidizing agent that can oxidize the cobalt 2 plus? What is the cobalt 2 plus going to react with first? We need a stronger oxidizing agent. Yep, the more negative gets oxidized, absolutely. So the more positive must get reduced, and that must be the stronger oxidizing agent. Strong enough to oxidize the cobalt 2 plus, or can be reduced by the cobalt 2 plus. Yeah, absolutely. So good. So that one goes that way, and that gets reduced. Okay. Now, I hate left right because it's meaningless in a way. So the way that I do it is EOX plus E-red. Now, this thing, we're given the reduction potential by convention, but what are we doing to the cobalt 2 plus? We're going this way, look. The cobalt 2 plus to cobalt 3 plus plus an electron. So what is the electrode value for that? It's not plus 1.82, it is good. Lovely. The S2O8 2 minus peroxide disulfate plus the 2 electrons goes to 2SO4 2 minus. That gets reduced, so that goes in the normal direction, and that's E red. So what's E cell going to be? So E cell has to be what? If we're just going to add these two numbers up. Not 3.83, it's going to be plus 0.19. So, next thing is that feasible? It's feasible, for sure. Definitely feasible. Okay, we good with that? That's the first thing that happens. But we know it's a catalyst. So what has to happen? The fact that it's a catalyst, it gets regenerated, right? So it goes back to CO2 plus. How do we make it go back to CO2 plus then? Feasible because positive, correct. E cell has to be positive for it to be feasible. Don't need to know about why, but it just has to be. Okay, it gets reduced back. So what's reducing it? Do we have a more negative species? The iodine gets oxidized. Good. So this is going to be minus 0.54 plus 1.82, which gives me plus 1.28 volts. Feasible. Sorted. Do we see the logic there? So the cobalt 3 plus is a... Why do we use minus 1.8? Why do we use minus 1.82 and not 1.82? Okay. What, for the first one are you asking? So in the first one... Yep, absolutely. The most negative one in this case, so this is more negative than that one. So because this is more positive, it can oxidize the cobalt 2 plus, okay? Because that's a stronger oxidizing agent, it gets reduced. So basically that thing is taking electrons, forcing this thing to give it out. So if it's forcing this thing to give it out, we're making the cobalt 2 plus going the opposite way. But by convention, we're given the reduction potentials. However, we're making CO2 plus go to CO3 plus, so we have to flip. Just flip it for the negative electrode. Nathan, you're confused. How is E cell not reduced minus oxidized? Reduced. It works the same way. Hang on. How can it? If it was reduced... I think you're using right and left though, aren't you? Cool. Use right and left, whatever. Use right and left. Yeah, because actually, if you think about it, look, in the right one, it's cobalt 2 plus going to cobalt 3 plus, right? So that's oxidized. And the right-hand one's going to be this, isn't it? Ah, okay. It's the same thing. It's the same thing. Yeah? Cool. Let's move on from this. This is another required practical. Bit of a nasty question, really. Let me know if you fancy it. If not, I understand. Have a read of that, people. Why is this question so long? You were looking through this today? 6 marks. I can't really. So what are we doing? Got 20 minutes left. Are we allowing it? Because we're pretty much done then. You got to be awake for this question. So you've got a choice. I'm going to give you a choice. So we can call it a day here, or I can do a tiny bit of chromatography. We don't have the capacity. I know this will come after tomorrow. How do you know? We don't know. This is why we're planning, like, for any eventuality. But I'm just going to say we've got a choice. So we can do this, or we can do a bit of chromatography and some mixture just from scratch. Tell me. And you do need sleep, you're right. Yeah, I've done the answers. I'll send them to Holika as well. If we don't do it, that's because of you. Complain about yourself. I'm giving you a choice. The choice is yours. Can we do this question and call it a day? Right. Come on then. Do this and chromatography. I don't mind it, Hamza. Right. A bit of a shout out before we do this. Can you because Hokia has asked, can you please leave some reviews on Trustpilot, please? Yes, if I do this. Cool. All right. Hockey is asking, so I'll copy the link. I'll paste it here. It's for my headspace. It's not really for me. It helps the company. It really does. Okay. It's for the company. It's not about individuals. So let's do it. Okay. This is a tough question. Genuinely a tough question. I had to think about what's going on here because there are so many traps for this. So many traps for this. And I'm going to say chromatography, if you've got the Easter revision course, have a look at the chromatography on there. The DNA guys, you can just learn that stuff, yeah? I mean, I'll try if I got time after to go through nucleotides, but let's see how this question goes. So, oh, that's long. Okay, cool. So basically, we've got to show, this is a tough question. Tough. Design an experiment to show that the standard electrode potential for this funky ion is actually that. Okay, so you have copper 2 plus copper. You've got solid titanium oxysulfate. Okay, right. we know the... Okay, so we know the concentration and we know the volume of the solution. Right. Now, when we're doing standard electrode potentials, we'll start with the titanium oxysulfate first. What do we need the concentration of the solution to be? Yeah, we're using this to we're using this to verify that it's minus 0.88 because we can't be bothered to use a standard hydrogen electrode because it's hard to maintain it. Yeah, we need it to be 1 mole per decimeter cubed. So what do we know? We've got the concentration and the volume. So N equals C times V. So N equals the volume, which is 50 over 1,000, times 0.50. So let's work out what that number of moles is. Times 0.50, that's 0.025. Okay, moles. Where do we go next? Because we need to work out an actual mass here to dissolve this with. So, am I given the MR? Hang on, have I done something wrong? I could have done something wrong. I think I have done something wrong. Wait. I think I have done something wrong. Wait. Let me read the question. Okay. I've done something wrong. No. Forgive me. Right. Mistake. It's good to make a mistake. Yeah. Right. Concentration, we know, has to be 1 mole per decimeter cubed because it's under standard conditions. It's good to have a mistake and just own it. It was an error. So the concentration is set because it's standard conditions, okay? So the concentration has to be 1 mole per decimeter cubed. We're dissolving it in 50 centimeters cubed of solution. So that's going to be 50. Thank you. Cheers, Leo. Thanks, Dylan. Good luck, everyone. Somehow, let me know how it goes tomorrow, please. I am curious, and I want to know how you guys find it. So, we need 0.05 moles of the titanium oxysulfate, okay? Does that make sense? So then, to work out the mass that I need, I'm going to use the number of moles, and I'm going to multiply it by the MR, which is given to me in the question, which is that. So times that by 159.9. So I get a mass of 7.995 grams. Can I do another 30 minutes? I'll definitely try. I'll see how it goes. Right. I'm confused. Sorry. That's fine. I was confused. So, because it's a standard electrode potential, any ions that we have in our electrode have to be 1 mole per decimeter cubed because that's what standard conditions are. If we've got ions, they have to be in the concentration of 1 mole per decimeter cubed. So we need 1 mole per decimeter cubed of these ions. And to get 1 mole per decimeter cubed of these ions, so we're going to set it as 1 mole per decimeter cubed, times it by the volume that we're going to have, that gives us the number of moles of oxysulfate that we need. In order to get that many moles, we need this mass. Does that make sense? So this is set by standard conditions. Yes? I need some feedback. Does that make sense? Sweet. Okay. Thanks, Robbo. Okay. So what we're saying is, let's look at it this way. So if I take 7.995 grams of oxysulfate, why work out grams? Because it's actually telling us how to do the experiment so we get a solution that is 1 mole per decimeter cubed. Thank you, everyone. We really appreciate it. This isn't for the strip of titanium because when we're doing a standard electrode problem, we need a strip of metal. So we've got a strip of titanium and we need it in the solution of the ions that are to be tested. So here we need a solution of TiO2 plus AQ, and that has to be 1 mole per decimeter cubed. Thank you, everyone. We really appreciate it. Don't say I, we. So thank you. It makes a big difference. So cheers. Els, does that make sense? So in one of the pots, that's what we're going to have. So we need a metal, and if we've got the ions, it has to be 1 mole per decimeter cubed. And to get 1 mole per decimeter cubed, we've got this mass, and we're dissolving it in 50 centimeters cubed of that solution. Okay? So we've got the 1 mole per decimeter cubed sorted. Okay, in the other pot, the grams is for making the solution exactly. Okay, in the other pot, what are we going to have? So we've got copper 2 plus and copper. Yes, I tell you what, I'll just redo it. I'll redo it, okay? I'll redo it here. Cheers, Mohammed. Thank you. Okay. Right, where were we? Okay. So, let's do this. So that's going to be, yeah, copper there. Okay, let's draw this together. You should have a blank page. So actually the most positive electrode is going to form the right-hand electrode. So that's going to be copper. And copper, if I'm not mistaken, is 0.34 volts. So we got copper 2 plus ions, 1 mole per decimeter cubed, and we got a strip of copper. Okay, in our other pot, the more reducing electrode is going to be the titanium because it's more negative. So we've got a strip of titanium metal and we've got TiO2 plus. Okay, and we need 1 mole per decimeter cubed of this solution. And to get 1 mole per decimeter cubed of this solution, we used a mass of 7.995 grams. I'm going to, but I'm just talking around it because there's a fair bit to do. Only if you annotate them. Only if you annotate them. So we'll talk about the prac in just a second. So I guess if I was talking about it, I'd first say weigh 7.995 grams of the titanium oxysulfate. Dissolve it in 50 centimeters cubed of acid. Transfer it to a volumetric flask and make it up to the mark. Does that make sense? So that's what I would first say. Yeah? And then you take a piece of titanium, place it into its solution, standard solution of each. Exactly. Exactly. So do you want me to write down the steps? I'll write down the steps. So weigh. It's probably worth saying what you're going to use in the salt bridge for sure. So weigh 7.995 grams of TiOSO4. Dissolve in 50 centimeters cubed of H2SO4. Make a standard solution or transfer to a volumetric flask. Yeah. So transfer to volumetric flask. You don't have to say 250. You don't need to say that. You just have to say transfer to a volumetric flask. You get different size volumetric flasks. It's not always 250, okay? So that's all we need to say for now. Yeah? Does that make sense so far? Are you with me so far? Cool. And actually, probably would reword that actually, because thinking back, I would probably dissolve in acid. Doesn't actually say how much. Make up to a volumetric flask of 50 centimeters cubed is what I would say. Okay, cool. Does the working out on the other page explain why we use 7.995? Yes, it does. So if I go back, the working out explains we need a concentration of 1 mole per decimeter cubed. But remember, the volume of the solution is 50. So that gives us the moles of titanium oxysulfate times the moles by the MR. And that gives you the mass that we need. So what we're doing is this. Here is our titanium oxysulfate. We're dissolving it in some acid. And then we're making it up to a 50 centimeter cubed solution in a volumetric flask. Done. Okay. With water. Okay. So what are we doing next? Is everyone with me so far? So then we take a piece of titanium. So titanium, metal, dipped in a solution of TiO2 plus of concentration 1 mole per decimeter cubed. I mean, tell you what, I would probably, I think I would leave it like I've done here. React in H2SO4, acidified water or something. But yeah, add the acid, then make it up to the mark with water. That's the order actually I would do. Okay, do you have to scrub the oxide off? Well, it's titanium. Is it going to have a massive oxide layer on there? No, like we're just trying to get to the, I don't think you're going to get marks for it, but put it in, it's not going to harm you. Okay, right. All right, after we've done that, what are we going to do next? And you can talk about the copper side as well, then same concept for copper side. Okay, yeah, talk about the copper side and just say 1 mole per decimeter cubed of copper sulfate solution or whatever it was in the question. I can't remember now. But let's say you've got this, yeah, exactly, connect them. How do you connect them? What type of voltmeter? You have to use some wording here. See you later, Mohammed. Take care. High resistance voltmeter. Good. You don't want any current flow. So use a high resistance voltmeter. You don't want any current because that's going to give you. You can do the washings with water, Fatima, for sure. That's fine. Doesn't matter the order really, but with water's fine. Okay, so use a high resistance voltmeter. Now it's not a full circuit. Why is it not a full circuit? What do we need to do? Because at the moment we've only got it going in one direction. It's not a closed loop. Summer, thank you. Good luck. Let me know how it goes. You need a salt bridge. Good. So I'm going to do that in a different color. Okay. Lots of people saying, what should we use in the salt bridge? I would probably say KNO3 always. Okay. Not so that the electrons can flow, so that the ions move. So ions move, but it completes the circuit through ion conduction. Okay, cool. So then what are we going to do? and then we're going to record the voltage. Okay, Charles, good luck. So, the question was, demonstrate that the TiO2 plus electrode is minus 0.88. If this is true, if this is minus 0.88, what should E cell be? E cell will be, if titanium TiO2 plus is minus 0.88 volts, what is it going to be? Let's see if we can figure this out. Not 0.88. So this cell is minus 0.88 for the reduction potential, and this cell is plus 0.34 volts. So what's E cell going to be? You can do it right take away left. So right take away left is going to be 1.22. And bingo, there you go. Sorted. Amir, I think it tells us it's plus 0.34. It tells you. No worries. That's how you do it. So it's actually not that bad. It's not that bad, is it? No, it wasn't, but it was quite... It's just because they've used this weird iron, but it's not really that bad, and you had to do that math step first, but not terrible. Okay. Shall we leave it there? We've been going for 6 hours, 40 minutes. Well, it was to... So the question was actually, design an experiment that the standard electrode potential is minus 0.88. Well, if that is minus 0.88, E cell should be 1.22. Yeah, does that make sense? I'm going to send it to Holika now, okay? I reckon if you label it and you explain each step like I'm doing and it's properly annotated, 100%. You guys deserve it, because really, a lot of you have had exams non-stop. You've had a maths exam and you're still here. So you deserve a lot of the praise. In fact, all of the praise. So well done. Good luck. Remember to leave some reviews, please. I really hope it was useful. That's the main thing. And well done for just gritting and just getting on with it. Go in there with bags of confidence, like doing a set of 10 on the squats, okay? Don't worry about the next rep. Take it in singles. See how you get on. All the best. I'm rooting for you guys. Come on. Right. I will. Don't worry. Thank you guys so much. You guys are superb. I used to have a teacher called Mr. Grattan. Weird. There you go. Thank you so much. I'm rooting for you guys. You guys are solid. Let's go. See you later. Greetings. There you go. Laters. You've got this. You've got this. Ta-ta.